大家好，欢迎大家来到今天我们的这个报告，是由极致俱乐部和英国科学社区共同举办的读书会第3季，关于这个因果推断。然后由于主讲老师是这个佩尔老师，所以我们今天要就是全程是会用英文来进行介绍的。Okay, so hello everyone, welcome to our lecture today. Today our lecture will be given by Professor Per Johansson. And first, I will give a brief introduction of the lecturer today. Okay, so Professor Per Johansson is a professor in Yale Mathematical Sciences Center at Tsinghua University, and also he's a professor in Department of Statistics, Uppsala University and IFAU, and he's also a co-opt member of the Nobel Prize in Economics. His research interest is in the broadly defined causal inference, and it's an honor to have Professor Per to give a lecture today. And today we also have 4 invited guests here. They are Professor Jinli Zhang from Peking University, who is she's doing Bayesian demography and causal inference data and text mining, and Professor Wang Miao from Peking University as well, who is doing causal inference and missing data analysis and artificial intelligence. The third invited guest is the Professor Yue Hu from Tsinghua University, who is doing political psychology and political linguists. And the last guest speaker is Professor Jianming Huang from Princeton University, and he is working on topics about causal inference and the sciences of science. Okay, so today we'll start by a lecture by Professor Per Johansson, and then there will be a screenshot for everyone, like a big photo together, and then there will be the discussion part. And for all the audience, if you have any questions, please, you can just type in the chat, and we will discuss this after Per's lecture so that it will be a smooth one. Okay, let's welcome Professor Per Johansson, give us the lecture topic as natural or quasi-experiments in economics. Welcome. And Per, you may start to share your screen. I will stop sharing mine.
Okay.
Okay, welcome.
Thank you. I guess there will not be any comments during my lecture, which I think is a little bit sad because I think sort of feedback during the talk is beneficial for me, of course, but it's hard. I can understand it's hard with this kind of Zoom meeting. So the title of this talk is Natural Quasi-Experimental in Economics, and this is, I mean, the title is affected by the fact that this year's prize in the this year's Nobel Prize in Economics was given to this area of natural quasi-experiments. So I thought I could give a brief talk about how economists are thinking about natural quasi-experiments. So that was the fact. This is the background. First, I mean, one needs to think about what economics is, and one needs to define it in some way. And this is my definition, and I think most people would agree with it. Economics deals with how we efficiently create and distribute goods that are valuable for people. So this is, I think, with goods, I mean a lot of things. It could be healthcare, it can be also environment and things like that. So it's also about scarce resources, and that's where you have efficiency. So I think all economists today are neoclassical economists. So all economists have the same way of thinking. There is no Marxist economist any longer, I would say. If they exist, they are very, very few of them. So economists believe sort of in market solution to some extent, but also we deal a lot about market failures, for instance, with environment. So there need to be restrictions, of course, and there is also this kind of thing with political economy. But in the end of the day, I think all economists believe in this neoclassical idea about economy. And the neoclassical theory, it deals with understanding human firm behavior. and what that kind of have effects on policies for humans and firms outcome, and this is microeconomic metrics. So we would also we have the theory, the sort of economic theory is this neoclassical theory, and that starts with human behavior. Okay, so we have human behavior, and today we are also focusing on understanding human behavior empirically. This was not the case like 30, 40 or 50 years ago, because then we did not have this individual data. Now we have individual data, and it has been more and more focus on understanding human or firms' behavior and effect of policies on humans and firms' outcomes. And this is microeconometrics when you are doing something like that empirically. The economic theory is known, we say it's ceteris paribus, or all else equal. This implies empirically a univariate variation of one variable, the cause on an outcome. For example, the theory says that education should increase income. Okay, education is thus the cause and often referred to as the X variable if you do an empirical analysis. And income is the outcome, often referred to as the Y variable. And when I say theory says, I mean, it's not really a theory. The theory is that education increases productivity. So productivity, and if you have a market solution, well, then if you are more productive, you should earn higher income. That's the theory. There is also another theory saying that education is mere a method for selecting individuals. Education doesn't increase the productivity, but it increases sort of the possibility for the companies to select people. They select the most able. Doesn't really affect the productivity. So there are two competing theories. Both says that education should lead to higher wages, but one say that education is not increasing productivity. This theory has been tested, and it shows that education indeed increases productivity, as far as I understand. The tradition in empirical analysis is to frame the theory into a regression model. So economics, when it comes to sort of empirical work, it's all about regression models. In its simplest form, we have Y is a function of the X variable that we are interested in studying, and then you have an error term. And this is in the economics field, we think of this model as being a population regression model, a population or a superpopulation regression model, sort of the true model in some way. Not really true, but sort of true. To avoid misunderstandings, however, it would have been better to write it as Y is equal to beta naught, the mean value, and beta 1 and do X. That means that this reflects the theory of Y as the dependent variable and X as the independent variable. And this form of notation is used by this Julia Pearl, and I borrowed from that, do X. So it says that we have Y as a dependent and X as the independent variable. In experiments, X is manipulated. That means that we really have this do X by the researcher. That is, X can be considered as fixed, but in real life, that is when we are passively taking data from different sources, this is called observational data, then X can affect Y, Y can affect X. We have a third variable, U, that is unobserved, that can affect both X and Y at the same time. So U is a variable that researcher cannot see, for instance, innate ability in this schooling example. So this is, for example, people with high education may have higher innate ability than people with low or no education. That is, there is an ability, that is, their ability differ also absent the education. And when I talk with Donald Rubin about this setup, he cannot really understand this second part, that X can affect Y, but Y can affect X. And no, that is impossible. You can never have it like you have both. You cannot have this reverse causation, because you know when you are measuring things. But this has to do with what kind of data you have at your disposal. So this reverse causation things has to do with, for instance, if you have data aggregated at yearly levels, well, then it could be that X have an effect on Y, but Y could also have an effect on X. In an experimental situation, of course, then you know that you are manipulating X, so then there is an effect on Y. But with observational data and with the type of data that we have, if it's aggregated over longer time periods, it may not be so clear at all. I will come back to this because this was an issue discussed a lot in and this was the development of econometrics, I would say, in the 1930s, 1940s. Was how to deal with this kind of reverse causation problem in a simultaneous models. These three relationships provide a statistical relationship between X and Y, that is the covariance between X and Y is different from 0. Thus, if 2 and 3 are present, well then beta 1 which is the covariance of X and Y divided by the variance of X, could be a biased estimator of the causal effect of education on income. For example, if innate ability is positively associated with income, then beta 1 will be biased upward in the comparison with the structural beta 1. So in economics, we talk about structural parameters sometimes. And in this very simple model, we have Y is a function of X only, but then beta 1 is the structural parameter. This is a lot discussed in the economic literature at the moment, so that is distorted selection effects. I just wanted to have a very simple example of this kind of selection effect. A researcher wants to answer the following question: are individuals getting healthier by hospital visits? The researchers receives data on the health status of people who have and who have not been hospitalized in the past year. So we have hospitalized in the past year 7,774 individuals, not hospitalized. You measure the health status with 1 being poor, 5 excellent. Well, you get a mean outcome of 3.21 for this group, and then you get 3.93 for this group, and then you have the standard error like this. So it's lower among the people that have been hospitalized. You are measuring the health after they have come out from the hospital. People who have been in hospitals have significantly worse health than people who have not been in hospital. Is it then bad to visit the hospital? No, of course not, because there were sick people who were looking for a hospital in the first place. Economists call this selection or sorting into treatment. So we are sorting or selecting into treatment. So when you hear economists talk about selection or sorting, this is what we mean. So probably the people who visit hospitals were healthier after the visit than they would have otherwise be. So when you think about causality, you need to have the counterfactual scenario, that is, think if. Yeah. So empirical strategies using observational data should make it clear that the variation in X used in estimation is outside the decision maker or agent's control. That is, an observational study should have an identification strategy. An identification strategy relies on economic theory, except when the variation in X stems from a randomized experiment. And this is, I mean, when I talk with people in economics, they don't think we are using economic theory when we talk about identification, but we do indeed. We have this perspective of optimizing agents when we think about empirical problems. And in other fields, they don't have this kind of perspective, which means it can be quite hard to discuss with areas in other fields. So I have been sort of lecturing at Karolinska Institute, for instance, in Stockholm. And when I talk with these people in health area, they did not understand what I was talking about when I talked about identification, which I thought was so apparent. But since they did not have this mindset that the economists have, they could not understand what I was talking about. So that was an eye-opener for me, also collaborating with people in health, in the area of health, and made it quite clear that when we talk about identification, it may not be so self-evident what we mean when we talk about this in other disciplines. So as an illustration, assume we are interested in analyzing the effect on earnings, Y, for unemployed individuals taking labor market training. So we have X is equal to 1 if we take labor market training, X is equal to 0 if we don't take labor market training. In this decision, we have two agents. So remember that I talked about sort of an identification strategy. Empirical strategy using should make it clear that the variation in X used in estimation is outside the decision maker or agent's control. So one needs to think about who is agents in certain empirical problem. Okay, so in this case, we have two agents, the Public Employment Service, official, and you. The decision, that is X is equal to 1 or 0, cannot be based on the Public Employment Service official correct expectation of your future earnings in either of the two states, that is, if you have this labor market training or not. Furthermore, if you as unemployed can deny the offer, or if you can leave unemployment as a consequence of the offer, these decisions cannot be based on your own correct expected future earnings. So an empirical strategy trying to estimate the labor market training effect should in some way try to figure out how is the caseworker, the official at the Public Employment Service working. Do they have restrictions? Are there differences between different caseworkers, how they are operating? If there are differences in how they are operating, perhaps we can use the caseworker's ID as an instrument, as an identification strategy. So there are many ways of thinking about that for identification. So as soon as you start to think about sort of design, you need to think about who is the agents in this decision. Adjustment for a set of pre-treatment covariates or confounders or control variables. So in economics, I think we mostly use the word control variables when we talk about this. In statistics, we talk perhaps about pre-treatment covariates. In medicine, we talk about confounders. But yeah, but in economics, most often when you see writings about that, we use the word control variables set. In a multivariate regression model like this, so you just add it, is not what we call an identification strategy. It's not an identification strategy. An identification strategy tries to understand which factors are important for the assignment to labor market training. And this was what I was referring to when I said we should understand how the caseworkers are operating. Are there restrictions? Do they do different at different public employment service? Different public employment services. and see if we can use that kind of variation. That's an identification strategy. With an understanding of the institution, we may find out which variation in X that is outside the control of the agents. In economics, multivariate regression is the workhorse. I said that when we started. We think of everything like linear regression models in the estimation. But one needs to distinguish between identification and estimation. Identification is a design, while estimation, mostly via linear regressions, is the analysis. So identification is a design, estimation is the analysis, and in economics, almost all analyses are done via linear regression. Maybe perhaps a little bit peculiar for many to think of it like this. I talked with Donna Rubin about this a lot, and I think in the beginning when we started to talk about that, he was quite skeptical about this, but I think he understands better now how economists are thinking. By randomly placing individuals in a treatment and a control group, one avoids the selection problem, that is the randomized control trial. If you have enough individuals, the group will likely be the same on average. Difference in outcome between groups must then be due to the treatment, now used as the conceptual mindset in non-experiment effect analysis, that is observational studies in economics. So the randomized control trial is the mindset, how we think about analysis. The fact that people are conscious creates problem in an RCT. Individual behavior change as a consequence of being understudied. This is called the Hawthorne effect. Could also be a placebo effect, of course. Hawthorne comes from a factory in USA where they changed the light. So I think this experiment was conducted in the 30s, 40s in USA, something like that. They had an idea that productivity would increase with increased lighting. So they changed the light in this factory and then productivity increased. But then after some time, the productivity reduced again. And then they increased the lighting again in the factory and then the productivity increased again. But later on, it went down again. And then they turned the experiment the other way around and decreased the light in the factory, and then productivity increased again. So when individuals are observed, we change our behavior. Individuals participating in a study, that is the experiment in this case, often wants to get the treatment, not the alternative, and that is a substitution effect. So we are conscious, and if I go into a study that where you have informed consent, because many times most often when you do a randomized experiment, you enter into this experiment because you would like to be treated, not to get the control. You would like to have a treatment. One example of this is the HIV epidemic, where people volunteered to be in an experiment to get medicine for AIDS. And of course, when they went into this experiment, they wanted to have an active ingredient. And it was later found out that people sort of they went to a pharmacy to see whether they got a sugar pill or an active ingredient. And if they got a sugar pill, well, then they tried to get something else and perhaps also live a more healthy lifestyle. So they changed the behavior. So that's sort of a substitution effect. So if you want to have a treatment and you cannot double blind that, for instance, labor market training, you go into this experiment because you would like to have a labor market training, because you would like to have improvements in your productivity. Well, if you are randomized out from this experiment and you don't get this labor market training, yeah, perhaps you try to find an alternative training program outside of this program, and that's a substitute for the labor market training that you would get in the experiment, but then you have another training, and that of course will lead to flawed estimates. Researchers who develop a treatment want to show that it's effective, and this is pure cheating. As a consequence, the individuals under observation and the research leader should not know that the treatment status, so it should be double-blind. Double-blind RCT or even triple-blind RCTs also hidden for the people analyzing the data, because there is also seen in the literature that if people know what is the treatment group and the control group, that could also affect the analysis. Only possible to estimate the effect against the possible alternative, for instance, the placebo treatment. So you need to give a placebo treatment, but also, as I said, with this example here, in the HIV experiment, it was a placebo. So they were given sugar pills and an active ingredient. But due to our conscience, humans' conscious, and it was a deadly disease. They could still sort of figure out if they have got these active ingredients or not. So it can also be with certain type of treatments and consequences of a disease, for instance, that also blinding could be, this experiment could be flawed. So how to give blinded placebo in a heart transplant or in a cognitive behavioral treatment therapy? That's a problem. So cognitive behavioral therapy, I hope you understand, it's psychological treatment for mild or moderate psychological disorders. Well, if you have an experiment where you would like to give this cognitive behavioral therapy, but not others, well, you cannot hide that, of course. And heart transplant cannot be hidden. On the other hand, it may not be a big problem because you are measuring things on mortality. Okay. So you are measuring whether a patient survived longer after getting a heart transplant than if they didn't get the heart transplant. So that is sort of, when it comes to this kind of experiments, you are measuring of things that perhaps individuals cannot really affect. But with cognitive behavioral therapy, many times they are measuring the outcome based on service. So they have subjective outcomes, and then they measure something like EQ5D. So that is how you are, a way of measuring your subjective health. If I know that I got cognitive behavioral therapy, I would most likely respond more favorable in these questions than if I did not get the cognitive behavioral therapy when I wanted to have the cognitive behavioral therapy when I went into this experiment. So measuring things via surveys and not being able to blind is a big problem with the randomized experiment, I would say. But if you measure it on mortality or something like that, it's a less of a problem, of course. If not blinded individuals, the potential outcomes of one unit may be affected by other units' treatment allocations. That is, SUTVA does not hold. Okay. You went to this lecture with Donna Rubin, so I assume that you know what SUTVA is. SUTVA is a stable unit treatment value assumption. So our potential outcomes are affected by the fact that we are in that we know that other peoples are also affected by are in this experiment, and our outcome is not measured as is not the potential outcome given the treatment, so that is could be a problem. The alternative to the randomized controlled trial is observational studies. The crux is that the individual's decision of treatment often is related to the outcome of the study. So bad health are most often the reason for a medical treatment. For instance, cognitive behavioral therapy, the reason you take cognitive behavioral therapy is that you have a psychological disorder in some way. And people not taking this cognitive behavioral therapy don't have the same psychological disorders as people taking cognitive behavioral therapy. Hospital visits, heart transplants, etc. So bad health are most often the reason for a medical treatment. That is, medical treatment could be the hospital visits, as we discussed just a few slides ago, heart transplant, and so on. So all observational studies should have a design, and with this design, I mean quasi-experimental studies. I talked about that. Today, the potential outcome framework with Niemann, 1923, Rubin, 1974, is the main philosophical framework in applied microeconomics. The framework brings clarity on what is estimated, for instance, an estimand. The estimand is often an average for a population of heterogeneous agents, individuals' response of one variable X on an outcome Y. For instance, the average treatment effect, this is the superpopulation expectation over the potential over the outcome under treatment minus the outcome under the no treatment. So this is the average treatment effect. So quasi-experiments, how to define that? A focus on the allocation of treatment. This is the Rubin-Causal model. So the Rubin-Causal model is a quasi-experiment according to me. I don't know if some economists would not agree on that. They think it's very strange, but it is. That's a quasi-experiment. That's quite clear. If possible, use variation in who receives treatment beyond the control of the individuals involved in the treatment assignment, for instance, doctors and or patients, case workers, and the unemployed, and so forth. Such variation can be found in differences in institutional rules, weather, geography, etc., where time and space create differences in treatment prevalence. Sometimes this variation may be deterministic, and then it's called a regression discontinuity design. For example, everyone over a certain threshold is offered a treatment. Studies using these types of design are called natural experiments. Well, yeah, it's a little bit, it's called like this in the economics, but originally, it was the nature. So the nature, and if you have, for instance, institutional rules, it is a little bit hard to argue that this is a natural experiment. So nowadays we call this sort of quasi-experiments. Variation may also be created by researchers, decision makers, denoted encouragement designs. So sending out letters randomly, for instance, is trying to affect people's behavior, is an encouragement design. So design-based observational studies are often called quasi-experimental studies. I, in some way, prefer perhaps design-based observational studies to some extent. But this is usually used sort of, yeah, sometimes, yeah, I think nowadays this design-based is more often used in the literature. So the design-based approach and things like that, but it's used interchangeable, quasi-experimental studies, design-based. Yeah. So usually when I give sort of lectures for students. I talk a lot about the Rubin causal model. The Rubin causal model, since Don was here talking, he talked about that. It was no need for me to talk about that. So I wanted to focus on this natural experiment and selection on unobservable methods in my talk. And this was also the focus of the Nobel Prize in economics. So I will just present 4 designs or estimators, the instrumental variables design or estimator, regression discontinuity design, difference in difference design, and the synthetic control. There are other ways. There are many other of these kind of quasi-experimental designs. So, but these 4, not the synthetic control, but the big ones used in economics are the IV, regression discontinuity, and difference in difference. So you have designs like regression kink design. You have staggered designs. You have timing of event design. So there are other designs out there that is also become more and more popular. Perhaps not the regression kink design, but I cannot go through all of them. And the focus for this year's prize was on this instrumental variables method, really, where Joshua Angrist and Guido Invens made a big contribution by adding the instrumental variables solution into the Rubin model framework. In general, what you will see is that non-parametric identification, as in the randomized controlled trial, of the average treatment effect is not possible. Now I repeat myself again. So I will talk about history and motivation of the IV. And this is things I have already talked about. To establish a causal relationship, we would ideally like to make a ceteris paribus comparison where we change the variable of interest, say a policy variable, by holding everything else constant. So that is what I started my lecture about, ceteris paribus changes in one variable. The problem is that such comparisons are difficult to make because of the various interdependencies in observational data. That is, daily life observations we have on individual and firm behavior. The initial response to this challenge was to model all conceivable interdependencies. With all a little bit, it's not, but with a lot of interdependencies. And this was the simultaneous equation models. So the econometricians of the 1930s, 40s built simultaneous equation models with the aim of controlling for the interdependencies. And these models could be very big. Economic theory was used to motivate the exclusion of some macro variables from certain parts of the model of simultaneously determined variables. And Hovelmo was received the Nobel Prize, I think, was it in 1988, I think, for his thesis written in 1943. However, the idea of identification in the simultaneous equation model had been solved by father and son, Philip and Seville Wright, almost 20 years earlier, but since forgotten. So I will talk about the ideas of the father and son, Philip and Seville Wright, and for people interested, perhaps it's so Seville Wright he was a statistician, I would say, or epidemiologist or something like that. So in some way, also this method with IV was also not perhaps, I mean, it was developed by Hovelmo, who was an economist, but it was sort of developed before, and Seville Wright was a statistician, I think, yeah, something like that. Philip, his father was an economist. The Wright's interest was on estimating supply and demand elasticity using data on quantities and price of goods. So it was aggregated data, no individual data. It was aggregated quantity and aggregated price of a good. They show that in order to identify the demand elasticity, one needs a variable not within the model that changed the supply. This type of variable is now known as an instrumental variable. So I will try to provide an intuition to the problem addressed by the Wrights and then turn to today's understanding of IV estimation in reduced form modeling. That is, we are mainly handling selection or sorting problem in the IV today. So in this case, and this is what we call reduced form modeling, because we don't have this reverse causation of variables as the Wrights were trying to solve. So example of this, we have an individual labor supply function. So, and we have a wage offer function, often also called an inverse labor demand function. So we have HS, and then I have it within W. I have, so this you can think about like a potential sort of, if you could move W like you do in an experiment, then what would this change? How would this change? So this was not how it was set up in its original form. They did not use this kind of potential that I have written here. Now I've written it more like to make it more transparent. It was not so transparent when it was set up, sort of in initial. It was just written it was not so transparently written as I think it's here in some way. So we have, this is hours. So this is hours of supply work given a wage. Then you have the offered wage for the hours of work when you have this fixed. This is fixed, okay. So this labor supply price shows how much a random person in the population would work at any given wage, okay. Then you have these variables as well that you are added. If we could run the right experiment, we could use ordinary least square to estimate gamma, because if we could give the wages, and then we would see how much people would change the supply of their labor, how much they would work. Well, then we could estimate gamma directly using data from this experiment. But we cannot run this kind of experiments, of course. We bring in the wage offer function to recognize that for retrospective aggregate data, we observe the pairs HI, WI, with WI not being randomly assigned. So in this case, HI is aggregated data. What I is, it could be time, so you have data over times, but it could also be across regions in the country, for instance. So you have variation across regions with this aggregate data, depending on sort of the labor market and things like that. So you can have variation over time and variation over regions to try to estimate this model. So the data could look like this. So you have wage, and then you have weekly hours of work. So you have a variation. The variation could then be over perhaps some regions, or it could be over time. So you have observed these dots in the data. You have these kind of data dots. So we need to assume something about this. So what we do then in economics, or what they did, was to assume that we observed equilibrium hours and wages. So all these dots were equilibriums. So equilibrium solutions to this market that we have. Okay, so here is then the supply, and this is then the demand for workers depending on the wage. So you have this. Okay, so you supply more of this with wage, more work is supplied if you increase the wage. Okay, and then you have different levels here. Well, if you then can have a shift in the supply that shifts up like this, so you have something outside of the system shifting this out, well, then you can identify the demand function. And if you have shift here in the supply, if you have shifted the demand like this, then you can identify the supply. I hope you see that. Sort of. This is in some way exogenous shifts in supply, exogenous shift in demand. Question is if they are. So what we say then is that under this assumption of equilibriums, the data are generated as this. So this is now the data. In the unusual case, we assume that the elements of x1 and x2 are exogenous. That means that they are independent with the error terms in this regression equations in both equations. If the set x1 differ from the set x2, so if these two sets differ, then gamma 1 and or gamma 2 are identified. The variables that are unique in each equation serves as instrument in the other equation. So if you have one unique covariate here that is not in this equation, well, then this serves as an instrument for estimating gamma 1 here. And if you have one covariate that is unique in this equation, that serves as an instrument for identifying gamma 2 in the other equation. So identification and estimation of both gamma 1 and gamma 2 requires at least one instrument in each equation. Let the focus be on estimating gamma 1. So assume x1 is smaller set than x2, then we would estimate this model where you have w here. So we are interested in estimating this, and x2 is a bigger set than x1. Well, this means that we have some variables here that is not in this. But what you do then is that you estimate the model for the wages using all the covariates that we have available. Then we use this predicted value from this estimated ordinary least square equation model as an exogenized wage in the least square equation. Thus, we plug this predicted value here into the labor supply equation. And the ordinary least square estimator on this model here is known as the two-stage least square estimator. So, okay. Now, so I hope perhaps, so this method, this shift here is sort of meant to show these exclusion restrictions of the x1 and x2. So one variable here in the supply equation is then shifted due to that we have another variable in the other equation. So this is what I mean with the x variables. The x variables are sort of giving this kind of shift. This is the intuition for it. Okay, assume interest is in estimating beta 1 in this very simple equation now. So now we don't think about this simultaneous equation model anymore. This was sort of very popular in in the 60s and 70s as well, and also early 1980 to try to estimate these models, but it didn't work out well. So economists basically have left these kind of models. There are some times we try to do it, but not to the same extent as it was done in the 70s, 1970s, where they put up quite large models, and it didn't really turn out. It was an empirical failure. It was a theoretical success, but an empirical failure. So you cannot have too complicated models. And today we are more focusing on trying to estimate these kind of reduced form models, as I said, and this has to do with acknowledging for selection. So assume interest is in estimating beta 1 in this equation. And here I again say that, okay, I don't have any sub-index here, okay, on WI or something like that. This is a population regression model. So in economics, we always assume random sampling. And this is the population regression model that we would like to estimate. Okay, but that omega E in this assignment equation, WI, okay, this arrow term here is correlated with UI in this structural model, reduced form model, but also structure. The beta 1 is structured parameters. Then ordinary least square on 2 would be a biased estimator of beta 1. Okay, so if we just run this regression here, where this is a treatment variable now, not the wages, this is a treatment indicator taking values W is equal to 1 or 0. So we are back to that. And then we have this assignment to treatment is a linear probability model like this. But if there is some correlation between omega and this U, well, then ordinary least square estimator or the population regression model would be a biased estimator of beta 1. Note that yi can be written like this. So I just plug in this delta naught, delta 1, set 1 plus this arrow term omega into this equation. So we can always write it like yi alpha naught plus alpha 1 set I, and then you have epsilon I. So alpha naught are these, that is the delta naught, beta naught, and gamma naught, and then you have alpha 1 is equal to beta 1 divided times delta 1. Thus, if we first estimate 3 and 4, so we estimate this is known as the first stage in econometrics or economics. This is the first stage like this, and 4, this is known as the reduced form. This is known as the reduced form, and this is known as the structural model, so even though it's reduced. Then we can estimate beta 1 as being simply the estimate from this reduced form divided by the estimate from the first stage that you have here. This is the Wald estimator, when you take the ratio of two coefficients. In this situation, one instrument and no covariates that we have needed to include into this model. The Wald estimator is equal to the two-stage least square estimator. So they give exactly the same result. With the two-stage least square, the predictions from the ordinary least square on 3, that is this. If we estimate this with ordinary least square, we can plug in, as we did with the simultaneous equation models, plug in the predicted values here into this model here. Then that is the two-stage least square. So The Wold estimator, that is the ratio of the two coefficients, is equal to the two-stage least square estimator. Well, with the two-stage least square estimator, the prediction from the ordinary square on 3 is used as a regressor in 2. EV and selection, just how this could be seen. So this is an encouragement design, a paper from Pervert and Hebel, who were interested in estimating the effect of smoking on birth weight on children. So we have an outcome that is a child's birth weight. We have an instrument, a letter sent or not to randomly, sent or not randomly to smoking mothers with information about the danger with smoking. We have a treatment that is W is equal to 1 if a mother stops smoking, and W is equal to 0 if the mother is still smoking. 20% stopped in the group that did not get the letter, while 43% in the group that got the letter stopped smoking. So this means that the first stage estimator is equal to 0.23. So if you had estimate this, well then delta 1, the estimate of that would be 0.23. From the paper, we get that the reduced form estimate of alpha 1 is equal to 98. So having the letter sent to you increased the birth weight with 98. But since this had only an effect of 0.23 of women actually stopped smoking, the effect on stopping smoking is much bigger, because it didn't, all mothers in the group that got the letter did not stop smoking, and also mothers that did not get the letter stopped smoking. So this is an example of a randomized experiment with non-compliance. I mean, since this is not an experiment sort of telling them to stop smoking, you cannot, but this is a randomized experiments with sort of incomplete compliance in different ways. So the effect of stop smoking is much bigger, so it's 426 grams. So that is an increase in birth weight with around 426 grams if quit smoking. If we allow for heterogeneous effect from the treatment, what would we really be identifying is the question. So here we have a model. This IV model assumes that everyone has the same treatment effect. We have beta 1 here, but perhaps it would have different effects. The effect for some mothers could be on the child's birth weight could differ from others. What would be the case in that? What would happen then? An IV today is by many, or all labor economists, I would say, defined as a variable that affects treatment, but is itself unconfounded and does not directly affect the potential outcomes. And this was sort of, Imbens and Angrist was the first one to put it up. Then you have Angrist, Imbens, and Rubin 1996 that had more impact in some way of changing the attitude on IV estimation. But Imbens and Angrist was the first paper. Imbens and Angrist 1994 examined how IV estimates should be interpreted in the situation with heterogeneous effect. They show that identification of average treatment effect in a well-defined population is only possible under strong assumptions on the individual treatment effects. A weighted local average treatment effect is possible to identify under weaker assumption, because in this original paper, Imbens and Angrist, they had a continuous instrument, not just a discrete instrument as I had here in this case. In this case, we had the discrete instrument, set I is equal to 1 or 0. In their setting, they had the setting of a traditional IV setting where the instrument was also allowed to be continuous. So they derived what they denoted as a weighted local average treatment effect. With the binary treatment, the late estimate can be estimated using the two-state least square estimate. The meaning of late is best understood using the language in Angrist and Imbens and Rubin. And I'm not really using exactly the language, but to some extent, I will try to just give an intuition for what we are doing. So for a very clear, clear definition of it, you need to read the paper really. They frame the estimate as the average effect in the population that changed the behavior of being treated as opposed to not treated as a consequence of a binary instrument that is an effect for those who comply. So they were very clear on for which population the treatment effect was identified. Let Wi set be the potential treatment given set is equal to 0, 1. So this is the instrument set, Wi set. I hope you know now the potential outcome definitions because Donna Rubin was talking just a couple of weeks ago. And let YIW be the potential outcome given W is equal to 0 and 1. So we have an instrument, we have a treatment, and I don't use exactly the annotations because I don't have time to go through all the assumptions here. But I think I will also try to just provide an intuition what they are doing with this notation. So we assume that the instrument is independent of the potential treatments. So you have two potential treatments depending on the level on the level of the instrument. And it's also independent of the potential outcomes if you are treated and not treated. The probability that you are treated given that you get set is equal to 1 differs from the probability that you are treated than if you have set is equal to 0. That is, we have an effect of set on W. And this is the first stage in the model I talked about before. You have also that the W, the potential treatment is bigger or equal to the potential treatment and the set is equal to 0. So this is then defined as nodifiers or monotonicity. In the Angrist Imbens Rubin paper, they talk about nodifiers. In the Imbens Angrist paper, they talk about monotonicity. So it means that the instrument cannot shift individual sort of in different directions. So this is for at the individual level. So there cannot be any defiers, no defiers or monotonicity. So this is So for instance, in the smoking example, the mothers that did not get the letter, the mothers that got the letter, we cannot assume that there cannot be any situation where the mothers who got the letter would have been quit smoking if they did not get the letter. But when they got the letter, they did not stop smoking. So that is not possible. Under this Sutwa assumption, the observed treatment is equal to W0 if you in this case did not get the letter. It is equal to W1 if you got the letter. So this is sort of we need to have that assumption. This is also the Sutwa assumption. So you can say that the observed outcome can be written as the Y0 if you are not treated, and Wy is equal to Y1 if you are getting the treatment. And you can write it like this. Okay, I just plug in this for the observed treatment into this. So I just plug in the observed here and here, and I get this complicated equation, and then I get alpha naught times zi, that's here, wi minus wi0, y1, y0, and then I have this error term where I simply move this part into the error term and remove the mean. So alpha naught is the mean in this sample. So see this, I take the expectation here of this first part, that's alpha naught. Then the error term here is equal to this part minus alpha naught. As omega I is independent of set I by assumption 1, so all has to do with this assumption 1 here, set I is independent of that. This means that we can regress y on set to get the causal effect of set on y. And here you have a heterogeneous treatment effect, because here you have the heterogeneous treatment effect, but it's also a consequence of the potential outcomes, the potential treatments here. So, but we can always say under assumption 1 that this model here, this alpha is a causal effect, okay, under assumption 1. If you have a randomized experiment, which we had in this case with the smoking mothers, well, then this estimate from the reduced form model is a causal effect. Alpha then is the expected value of this guy here for those that are getting the letter in this case, for those with set I equal to 1. So this we can write as the expected value of y1 given that this is bigger than 0 times the probability that wi1 minus wi0 is bigger than 0. So this second line is obtained under assumption 1 and 3. So this is the probability that we are stopping smoking in our case. So this is exactly delta 1 in the above example. Okay, so in this example here, we have delta 1 is equal to 0.23. Okay, so this is possible to identify and can be consistently estimated by regressing W on set I, that is delta 1 above, and then we can identify this treatment effect here. So this late parameter is equal to this guy here. So this subpopulation that has these values, wi1 is equal to 1, wi0 is equal to 0 is denoted as compliers. These individuals comply with the assignment no matter what their eligibility is. That is, if they did not receive the letter, they would not stop smoking in this example. And if they receive the letter, they would stop smoking. So they comply to this letter in this case. So you cannot identify who is in this group of compliers, but you can estimate the complier treatment effect or the local average treatment effect. In the medical literature and in the epidemiology literature, we are talking about the complier treatment effects today rather than the local average treatment effect. But in economics, it's constant. We are only talking about the local average treatment effect. So the key result is that under the 3 late assumptions, the usual two-stage least square estimator without controls for X consistently estimate this late parameter. One criticism of this late parameter is that it is a treatment effect for an unidentified segment of the population. We do not know on the basis of observing yi, wi, zi, whether unit I is a complier or not. Consequently, the late may not be externally valid, that is, it may not apply to evaluations of other programs, even if the population is the same. So yeah, this was heavily criticized in the when they started with this. When they came with this, you should read but people who are interested, you should read the comments to these papers when it was published. Jim Heckman, Nobel Prize winner in 2000, was extremely critical, saying that we cannot learn anything from this complier treatment effect or local average treatment effect, because it has no policy value. All they did was to show what is possible to non-parametrically identify. So I think the critique was very unfair. It was very unfair. But that was yeah, it was very criticized. With this late estimator and with the two-stage least square, there are problems with pre-testing. What yeah, I should I skipped a lot of this. What should I? Okay. You see, you have this first stage here. You have the instrument and you run a regression on the treatment like this. Okay. Then you have an estimator here, alpha 1 divided by delta 1. If delta 1 is close to 0 or estimated with very bad precision, the variance of this estimator will be very large. So in the literature, there is this, you cannot, if this estimate from a regression is not highly statistically significant, then the distribution of this estimator is not normal anymore. It's very far from being normally distributed. So standard inference cannot be done. And the recommendation sort of was that the F statistic, or in this case with one instrument, the T statistics need to be about 10. No, the F statistic, the T statistic needs to be like 3 point. Cannot just be sort of weakly correlated with the treatment. Okay. And this is what I mean with pre-testing. So with this type of estimator, there is problem with pre-testing, meaning that if the instruments are not strong, then you are not doing the analysis, and that influence the whole inference. What we learn from this kind of methods. So Bayesian analysis, which was suggested in Imbens and Rubin, are more effective way of doing inference than to do these ordinary least squares. That's I think Bayesian analysis may be a better way of doing this inference than this frequentistic way of doing the inference with these late estimators. Yeah, I should not have, since I haven't gone through this, it was a little bit hard to explain. I hope you understand. There is this idea that this instrument needs to be strong. If it's not strong, then you cannot do any analysis. And as a consequence, if you do IV estimations, you have a selection of papers that have very, very strong instrument, and that affects the inference later on. And so there is a problem with pre-testing with this type of analysis. Okay, regression discontinuity then. That dates back almost half a century by this paper by Tistelwaite and Campbell, and they studied the effects of merits award. But it was rediscovered by the economist van der Klauw in 1997. RD exploit discontinuities in policy assignment. For example, there might be an age threshold at which one become eligible for study grants, or an income threshold at which one become eligible for financial aid. The general idea is that we assume that units on different sides of a discontinuity are similar. The treatment status differ because of the institutional setup, and differences in outcome can be attributed to different treatment status. We consider here the sharp design, where the assignment follows a deterministic rule, and the fuzzy design, where the probability of being treated is discontinuous at known point. Under fairly weak assumptions, this consistently estimate a local treatment effect around the cutoff. As with this late framework, we are now setting up everything to the potential using this kind of potential outcomes. So we have two potential outcomes, y0 and y1. There is also a single covariate set determining the treatment W. Set is called a forcing or running variable. As before, we observe W, that is the treatment. We observe Zi and Yi, where Yi is again this switching mode. Is there some comments? No. Okay. So we observe y0 if you are not getting the treatment, and we observe y1 if we have the treatment. So this is under the assumption of the stable. This is under the stable unit treatment value assumption again. Assumption 1 is that the treatment is 1 if Z1 is above a certain threshold. So if this running variable or forcing variable is bigger than C, then we have a treatment. If it's below C, well, then W is equal to 0. So all individuals where Zi is bigger than C receives a treatment, and all individuals where Zi less than C do not receive treatment. Wi is a deterministic and discontinuous function of Zi. So assumption 2, and this is the critical assumption for RD, both for the sharp and the fuzzy designs. The conditional mean function, like this, conditioning on this running variable. So you have a treatment and a non-treatment. Okay, so you have this expected value. It's continuous at this specific threshold value. So the conditional mean function are continuous at this specific threshold value. Since Wi is a deterministic function of Zi, ignorability or independence, which we talk about in the Rubin causal model, holds. And I have not gone through that. The expected value of y0, conditioning on Zi and being treated, is equal to the conditional mean of being not treated Zi when Wi is equal to 0. So this is observed in the data. This is the identifying assumption. So we would like to have this, but this is observed in the data. And this is equal to the expected value of the potential outcome if you are treated, conditioning on Zi, for those that are not treated, is equal to the observed potential outcome for the treated, and this is observed in the data. However, the overlap condition, that is the probability that we are treated given set I, the running variable, is between 0 and 1, does not hold. So we don't have any overlap, as I hope you have gone through with Donna Rubin. The Rubin causal model consists of 3 assumptions. That is sort of the most important assumptions is the unconfoundedness assumption, but then you have the overlap condition, which says that you have comparable individuals with the same covariates based on the propensity score. So this is the propensity score as a function of the running variable, but this does not hold because there is no overlap at this threshold. There is no overlap. So, yeah. Therefore, we cannot, unless we are willing to assume a constant treatment effect or very strong functional form assumption, estimate an average treatment effect. So remember that when we started this talk, I assumed in the IV setting that we had homogeneous treatment effects. As long as you have homogeneous treatment effect, meaning that all individuals have the same treatment effect, well, then we can identify the average treatment effect, but that is a quite strong assumption. So with heterogeneous treatment effect, we typically have that the treatment that we have here, that this is the expected value y1 minus y0, conditioning on that the running variable is equal to c. That is the difference at the threshold value. This is the delta c. Differs from the average treatment effect because we believe we have heterogeneous treatment effect. So this is the average treatment effect for those at the margin of receiving the treatment. However, delta C is identified with only one key assumption, and that is that the conditional mean function are continuous at this threshold value. The interest on this parameter depends on the application. Generally, we sacrifice external validity from internal validity. So when we are using these RD designs in economics or whatever, we need to discuss how we can extend this estimate to be more general applicable in some sense. And there are methods of how to do that if you read into this literature. We can estimate the means at this threshold, the potential outcome under the north, and the expected value of the potential outcome if you are treated at this threshold separately by only calculating the means for those individuals in the small neighborhood around the cutoff. The argument is that these will be similar as in a randomized experiment at the cutoff because we have very similar set values. So what you do is you take a mean around these running variables of the outcome at this C plus delta, and then you divide, this is the number of individuals in this area of this, perhaps I need to have. So what I'm talking about now, this is a running variable we have here. So we have this just around this threshold, there is an increase in the outcome. So you can estimate the treatment effect around this threshold here and around the threshold here. Okay, so this is a linear, this is a regression discontinuity sort of idea. So you estimate simply the treatment effect just around these thresholds. I hope this is okay. So think about this. This is the number of individuals with the running variable close to the upper side of this figure that we had, and this is the outcome variables to the left of this regression of this running variable. So yeah, and see, is the number of individuals with set values in this interval. In practice, a trade-off between bias and efficiency. Few individuals close to the threshold, well then we have low efficiency and small bias. I hope you understand. I don't have any feedback. So if we take this here, just a few individuals on both sides of the threshold, like here on the one side, this is the treated, this is the non-treated. Okay, if we just take a few individuals here, so we have 5 individuals here and 5 individuals here, well, it's low bias, but it has a high variance. If you take these individuals in a larger set around this threshold, well, then you have more individuals, but then perhaps we get more bias. So it's a trade-off. If you run a regression model and you can use the regression model, well, then you use the whole data set to do the inference, but that could also lead to bias. Okay, so an alternative.
Hi, Per. Sorry to interrupt. I think we have covered like enough content here. Maybe you want to have a pause and have a little discussion. And if this goes too long time, we can finish the part next week if you like.
Yes,
So I guess which one you want to prefer?
It was too much. I agree. It was too much. It's good. It's better that we have comments, I think. Yes. And I'm
okay, so maybe you can finish the remaining of your lecture next week at the same time, and now we may start from the discussion.
I think it's enough with the discussion. Yes, I think that's good.
Okay. Yes. Okay, so I will just type in the discussion in the chat there, so so that you can also see. Okay, so the first question is by Professor Wang Miao, and
could I ask a question? Yeah.
Is it here? Yes. Okay.
Happy. Thank you for the nice talk. Actually, I have 2 questions. In addition to the one in the chat. So my first question is about the simultaneous equation model. So to me, it's hard for me to understand the causal interpretation of this model. So X can be the cause of Y, and Y can be the cause of X. So what's the causal interpretation of the regression coefficients of the simultaneous equation model?
Okay. No, it just have the same interpretation as we are in the simultaneous equation model. We are trying to estimate the marginal effects, like in a randomized experiment, even if we have this kind of reverse causation problem in the data. Yes. So the interpretation is sort of formula as a causal effect on Y, the causal effect of X on Y, and the causal effect of Y on X. Yes, it is a little bit strange. And I talked with Donna Rubin about this, and he says, I don't understand. I don't understand it. But this was the whole idea. And from Don's perspective, it is. But when I told him that you need to understand that you have assumed that you have collected data on the average wage in the labor market during 1 year, and then you also have the average number of hours worked in 1 year. Well, they are determined in the market simultaneously. They are determined. If you believe in the market solution, both variables are in some way determined by each other, as I showed you in this diagram. You see, you both have a supply and demand, and then you are measuring this at a given time period. And they really wanted to estimate this sort of, they believe they could do that. And theoretically, you can do that. You have identification. If you have certain areas, for instance, where the equilibrium solution differs from other areas with other equilibriums. So you have several equilibriums, and you have areas where you have a shift in the equilibrium. Well, then you can identify. And there is actually a very nice paper using the Rubin causal model, identifying the effect in a demand supply system. That's written by, I think it's Angrist, Imbens, and what is the third guy? So in that case, what they had was they estimated the demand for fish. So they used the potential outcome framework, and then they had changes. They used weather changes. So changes in the weather condition. So when it's very hard weather, the fisherman cannot go out in the sea to catch fish. So there is dramatically change in the supply of fish. Okay.
Yeah.
So then they can measure the price responsiveness of the supply changes using weather as an instrument. So that's they put up everything that you have this market solution where the prices are determined by supply and demand. And then due to supply shifts, due to weather, they can identify the price elasticity of fish. So Joshua Angrist and Imbens, they believe that, yeah, you can have this type of, as soon, I mean, since economists were interested in supply and demand,
yeah,
that means you need to be interested in the reverse. I mean, in that the effect could go in both sides. I hope, but the interpretation of the parameters are exactly the same as you interpret it as a randomized experiment. So economists have this idea about ceteris paribus. You should try to use the nature in some way to identify like an effect, like you would identify it if you could randomize the treatment really. So that is the idea. Yes. So it's not about dynamic models. So if you go over to sort of time series analysis, macroeconomics, monetary policy, in that setting, they have what they call vector autoregressive models, VAR models, if you know about that. Well, if you have this kind of system, then you identify parameters out of the lag structure. And then you have multiplier effects. And then you interpret things in a dynamic context, like, so the identification in that case comes from having lag variables. So you have a certain structure. Yeah. So this is related to the granular causality concept that is not the causality concept at all. Right. You have granular thing, yes. I hope that explains.
Yes, thank you.
In the simultaneous models, it's trying to really identify the causal effect as if you could have randomized both prices and the wages, wages and the labor supply. Mm.
Thank you. This is much more clear. Yeah. Thanks for the explanation. So my second question is the one prepared for the discussion. So after the Nobel Prize awarded to Carl Angrist and Imbens, so many people may ask why it is not given to Rubin or other people. Yeah. So my question is that not only this year's Nobel Prize, but also previous, like in 1989 and 2000 Nobel Prize was given to McFadden and Heckman. So many statisticians think that much of such kind of work in econometrics was paralyzed by statistical or biostatistical contributions to the analysis of observational data, missing data, and case control studies. So people may ask, are statisticians' contributions to econometrics or other applied sciences undervalued? Yeah.
No, I think the comment is highly relevant. Yeah, I'm an economist, but now I would call myself more a statistician. I'm doing mainly the work in statistics, and I like, yeah, so this price is in economics. It is in economics, and the whole problem, I think, for acknowledging other fields doing methodological work is that the economists are not using these methods. So if the economists were using these methods, then it's much more relevant to give a price. When it comes to Donna Rubin, there was an dramatically increase in using his methods. So I can't, since I'm part of this committee, I cannot tell everything that I know. But there is no sort of, I should not, I mean, I really think that Don deserves the Nobel Prize, but it is, one need to understand sort of, there is, it's a committee that take up this sort of suggestion for prize. Then you have the scientific community, which is like 400 people. In some way, they can say that no, we don't think this is prize-worthy. So it is a hard process, really. It is quite hard process. So and the most important economists are more theoretical than empirical. So many economists, they don't value empirical work at all. So there is also this kind of conflict between theoretical economists and the empirical economists. So the empirical economists could value a lot of the work done in statistics, but then you have sort of these theoretical economists that don't see the value of this, because many of the econometricians, they are using methods to, and developing, they are using like the Rubin causal model to develop this IV setting, for instance. For them, it was super important that they had the work done by Rubin. Otherwise, they could not have done this. So that was very important. But it's very hard to explain this to the theoretical economists about the important things that are about Tibshirani, things like that. Also, they don't. Because they are not into this field, so they can just see sort of, they cannot value what the econometricians are valuing. So no, it is still a prize how things have changed the attitudes in economics, not how it has changed the fields in econometrics. If it would have been how this kind of work has changed things in econometrics, then the statisticians would have received much more prizes. That's quite clear. So the econometricians are very appreciative of the development done in statistics. That's quite clear. Yes.
Okay, thank you. But, to me, I think econometrics is much close to mathematical statistics, right?
Yeah. No, at the moment, I think, I mean, we see things in econometrics very much like how a lot of the statisticians are seeing the same thing. No, we are very close, and to some extent, I think the statisticians doing causal inference are also, they start to become more like econometricians rather than the other way around in some way. I have this feeling that some of the really good econometricians into causal inference are influenced more by econometricians than the other way around. Yeah, that's when I read some of the papers, at least. Yes, that's my feeling. But there is this communication between the fields. And I see myself more of a statistician today than perhaps.
Okay.
Personally, I'm not so fond of all these asymptotic results. I think that's yeah, I'm less fond of that than sort of using. I mean, I think the ideas of Fisher and things like that are in many ways more interesting than all these kind of so using computers to do things instead of trying to derive asymptotic distributions, or also Bayesian models are more interesting than all this asymptotic theory. Yeah. But personally, yes. But there is a lot of asymptotic theory in econometrics.
Right.
Yeah.
Okay.
Yeah.
Thank you very much for discussion. Yeah. Thank you.
Yeah, thank you.
Okay, that's all my question.
Okay.
Yeah.
Are there more questions in the chat? Should I just read them, or I don't know?
I think we may start from the questions from the 4 guest inviters. We went 4 guests here. Professor, are you here?
Yeah. Can you hear me now?
Yes,
Yeah.
yes, it works now.
Great. Thank you for the lecture here. I actually have 2 questions. Both of them are basically conceptual. I'm a political scientist, so I'm not only interested in how the works how the techniques and method to help us to understand causal effects, but also we would like to know substantially how they are working in the real world. That relates to the concept of mechanism. When we talk about, as you just present, we're talking about something happened and the other thing happened. When we present that to my students, they will ask, okay, sorry, is that really works? And do you know it works in that way, but now the other way, even through the experiments, even through the quasi-experiments. So that's come back to my first question is, I would like to know, how do you think about the causal mechanism, and how it's causal mechanism just the steps of like step by step, we can see causal effects, and then that's a causal mechanism, or there are other efforts we can do? That's my first question.
Yeah, this is, you are asking about this mechanistic view of the world rather than sort of the potential outcome framework. Is that correct? Yeah. So, I mean, the way I set up this simultaneous equation model, I think that is a mechanistic setup originally. So I think they were influenced by this mechanistic ideas that comes, as I understand, from physics. So in physics, you have very clear theories, and you have also sort of that the environment, you can keep everything constant, basically. So if you have a physical theory, you have an environment where you don't have any heterogeneity, basically, so you can keep everything constant. Well, then you can think about causality in this mechanistic way. You see my point. But if you deal with humans or with animals, well, then you have large variation in the outcome. So in that sense, I think it's not useful to think about the world as mechanistic any longer due to the large heterogeneity in outcome and heterogeneity in treatment effects as well. So then it's much more relevant to use the model of Rubin to put up, or Neumann-Rubin, to put up the potential outcomes and really try to model the heterogeneity. Becomes more essential than to model the process. So there is no conflict between the mechanistic approach and the potential outcome as I see it, but the mechanistic approach is not useful when we are trying to deal with humans. That is how I see it. But I never talked with anyone about this, but that is how I see it. This is how I see it. So
yeah, thank you for the answer.
This goes also to the Pearl models. I really enjoyed reading the work of Pearl, but I think the Pearl is mechanistic in some sense. So when I read his book, I really enjoyed reading it, because that was like 20 years ago when the book first came out, because he put DAG models into the simultaneous equation models. So he was saying that this is how you should view causality, but it happens that you have these models already in economics. You have the simultaneous equation model in this, but then he continued to say that this is how we should view the world, but that's a mechanistic view of the world, and it doesn't, for me, it doesn't work with humans because of the large variation we have among humans in outcomes and in effects. We have so much variation, so it can be very useful to use this kind of DAGs as an illustration. But when we do the analysis, it's clearer if we use the potential outcome when we are trying to identify what we are really trying. It brings more clarity than the Pearl setup. For me, it does so. And it's interesting. I was an advisor of an economist that was doing political economy here in Uppsala, Fredrik Sävje. He is now in USA. I think he's at I don't know, but he's working with a political scientist in USA as well. And he is now basically a statistician. And I said to him when he was writing his thesis, the way you do this, I should use the Pearl models, the DAGs, because this is. And he refused to do that because he said, no, it doesn't bring clarity. And in the end of the day, he was right. He was right. Yes. So I tried to sort of encourage him to go into this DAGs because it is very difficult to build to describe things in political economy using these potential outcomes. It is, but I think he did a really good job in doing that. Yeah.
But since you already mentioned Judy Pierce, his graphing, so I just wonder, in your view, is that like Pierre and Rubin's model? They are talking exactly the same thing, but just in different way, in mechanism way, effect way, or there are some like logical or other fundamental difference between the two, in your view?
Yeah, I have not. As I told you, I was interested in the Pearl things like 20 years ago, and I have been doing some things on it. I have a paper that is in Journal of Causal Inference where we actually use the DAGs of Pearl, but that was just to show. It was to show about non-identification. It was a very simple way of showing non-identification in what we were doing there. So it would have been much harder to prove this using other math, I think. So we found this solution and we could show non-identification. And so I have used it. No, I think now when I read the Pearl's work, because I think it is in some way very naive. He believes we can set up, and it is like this the way I read it, it is like these ideas we had in economics in the 1960s, where we believe we can control for everything in the model. So it is sort of going back to the time when we were doing this simultaneous equation models. The DAGs don't allow for simultaneity. So that's a directed or cyclic graph. It's not direct. So you cannot allow for reverse causality in these models. but basically it is like you set up your model, and this allows you to control for everything in these graphs. But yeah, I don't. No, I should not. But I wrote. We had a reading group here in philosophy of science at Uppsala University, and then I read some papers, recent paper by Julia Pearl, and I could not understand them. So it's perhaps my lack of yeah, I'm not so mathematical, but I could not understand. So the potential outcome for me brings clarity in what I'm trying to do. Yes, it makes it more clear for me. But I think if you are more mathematical, perhaps the ideas from Pearl could be useful. Yeah, it could be, but no, I'm not mathematically skilled enough. That's what I should say, perhaps. But it is more close to this mechanistic view. And I don't believe the mechanistic view works when you are studying humans. It can work in other situations. So it is when you cannot say that this way of doing things doesn't work. I think it has to do in what context you are using. You see, if I'm doing something causal with machines, operating systems, well, then perhaps where you don't have humans that are involved, yeah, perhaps then that is the best way to do it. Then the mechanistic view is much better, much more useful than the potential outcomes. But as long as we are dealing with humans, then I think it's less useful. It's less useful. So I think it's context dependent on what problems you are trying to look at. So you should not say that, no, that is not useful, or this is not useful. I think it has to do with the context you are doing. And the mechanistic view has been very successful in physics. I mean, that's what they did when they said, when they were testing whether you have a heliocentric world or a world centered around the Earth. They were using mechanistic models to do that. And that was, of course, a success. And I guess Pearl would like that way of doing it. So you cannot say that this is good or this is wrong and this is better. It depends on the context. That's my attitude.
Yeah, fair question. Thank you. Thank you for the answer. Really impressive. That's all my question. Thank you.
Okay.
Can I add some comment? Yeah.
Yes, please do so. Please.
Okay, yeah. So Professor Hu just asked about the connection between Pearl's causal DAG and the potential outcome model. Actually, in 1998, Pearl and his collaborator had a paper on the connection between the three causal models, structure equation model using econometrics, and his causal DAG and Neyman and Rubin potential outcome model. So their conclusion is that these three models are mathematically equivalent. That is, given any one like structure equation model, you can rebuild it with DAG or potential outcome and do this the other way. That is just a conceptual. So in practice, when so each it depends on the context and background that you can choose different model for the application. Yeah, they are just mathematically equivalent. Yeah.
Yeah, no, I believe so too. You can write them. I mean, so it's very easy. I mean, but conceptually, if you take the simultaneous equation model used in economics, you can rewrite that into the potential outcome framework. Yes, you can do that afterwards. But the fact that you do this brings clarity what you are doing in the simultaneous equation model. This is important. So before Donald Rubin introduced the potential outcomes, all we had in the simultaneous equation models was these error terms. The error terms, we said, yeah, we assume that they are exogenous. Yes, but what does it mean? So by introducing the potential outcomes into the model brings clarity of what is in the error terms.
Okay.
You see.
Yeah.
So you can say they are mathematically equivalent. Yes, I agree on that. But the concept in itself is important to understand what is in this structured equation model and in this mechanistic view. I mean, in the mechanistic view, the error terms are just measurement errors. But when you are dealing with humans, the error terms are not just measurement errors. It's heterogeneity among the individuals. So the potential outcomes makes this clear.
Right. Yeah, I agree with it. Yeah.
So statistics is not math. It's not math. It is being clear in what you are trying to do. And of course, if I want to estimate something using rats, that's a much easier problem than when trying to estimate something dealing with humans, because we are conscious, and that complicates the analysis enormously.
Okay.
Yeah. Oh no, I think we say the same thing. I just added some. I just added a little bit. Yes.
Okay.
Thank you.
Okay, thanks for the questions. And Professor Zhini Zhang, you are muted now. You may unmute first.
Yes. Hello.
Yes, we can
hi,
hear.
Per. Yeah, nice to hear your talk. Yeah. Because you have talked a lot about this instrumental variable regression, right? So I'm just wondering, what is the remaining main challenges for using IV to do the causal analysis? Like especially when you were talking about that when the IV can identify late, and then there is because late is the latent population, and then it has been criticized by a lot of economists. And then how can the results of like IV analysis be used to guide future intervention? Can you?
Sorry about the second question.
How can the results of IV analysis be used to guide future intervention?
Oh, well, okay. Oh, yeah, that's a good question. Let me just think about that. 1 minute. Yeah. The first one, I mean, the problem with the IV, this is still studied with this. So if you remember, I said, but I didn't show that this first stage regression. So sort of the advice with the IV regression and the frequentistic approach, the asymptotic distribution can be very bad. It can be very bad. It can be far from normally distributed, and the variance is very large. And there was this kind of advice that the first stage regression, the instruments in the first stage regression, the F statistic of that should be bigger than 10. Nowadays, the advice is that the F statistic should be more than 100 for it to be a valid estimator. So that's recent papers showing. So honestly, I'm quite skeptical of the IV solution. So I really believe that if you want to use the IV, you should go over to maximum likelihood or a Bayesian analysis that was suggested by Imbens and Rubin, 2 papers in 1997, I think it was. That is has much better properties than these frequentistic solutions. So, but there is a large resistance in the economics community about Bayesian analysis. But I really believe that is what, if they believe in sort of, yeah, if one could convince them that this frequentistic modes of inference doesn't work, because it doesn't work, I think it would be better to have a Bayesian models. And since you are doing Bayesian analysis, I guess you would agree with me. When it comes to external validity, I mean, there is a lot of things done in the IV estimation, among others by Angrist, but also by Imbens and Rubin in the paper. So what they show is sort of who, even if you cannot identify who is the complier, you can identify based on covariates who is the group that is complying. So is it low income workers, for instance, if you have an experiment? Is it individuals with bad health if you have an experiment in the medical research? So you can identify who, even if you cannot identify the individual per se, you can identify for which groups you have a big treatment effect. And of course, if you can identify for which groups, who is the most likely to be a complier, then it's also possible to do external, to talk about external validity to some extent. So a lot of work now in the in economics is dealing with this, of estimating the who is. If you have a large set of covariates in your data, then you can identify who is, not exactly, but you can identify who is the most likely to be a complier. And for that, it's also possible to say something more about external validity from this. Did you think about, what are they doing? I mean, Robbins and others, they are doing this kind of things as well in the medical field. Do you have any? I guess, but I think there are people. I mean, this is how they are trying to handle this problem, that you are identifying it for a group that is latent, but you can still classify this group of this latent population based on the covariates. So you can learn much more than just to say that this is a compliant treatment effect.
Yes, I have seen that they are kind of work. And
okay.
Yeah, and the other things, because you mentioned the Bayesian model, and of course I agree that Bayesian analysis would be also, very useful in this context. But I'm just wondering, because there could be many like continuous IVs, right? So I wonder whether you have seen Bayesian analysis with the continuous IV instrumental variables.
No, I have not. I mean, the original paper, as I talked about, this paper by Imbens and Angrist.
Yeah, that's the banner, right? Yeah.
Yes, they had the continuous. And what they show is that you can estimate this weighted late effect. Yes. No, I have not seen that. That's interesting. Yes, that's interesting. I think, nowadays, as soon as you have a continuous instrument, people in economics, they are discretizing the instrument. So they are, instead of having a continuous instrument, we are discretizing that to say, below or above median.
I see.
Put it into this late framework.
Right.
No, but that's interesting, yes. And that would be easy to solve in the Bayesian model rather than in the frequentistic model, yes. I suspect, yes.
Okay, thank you. Yeah, thank you.
Okay, thanks for the question from Professor Zhang and Professor Huang Junming. He's
Hi,
from
Pearl.
Princeton and okay, great.
Sorry, go ahead. Okay, hi. Hi, I'm Junming Huang. I'm an associate research scientist at Princeton University. My background is a mixture of computer scientist and social scientist. I'm quite interested in applying statistics models like causal inference models in applications in social sciences. So I have two questions. So first, I'm wondering, in your opinion, what's the most interesting, most important open questions in potential outcome models that is not perfectly answered in the frontier study? I'm curious about this question because in the context of the recent progress on computational methods like deep learning and graph neural networks, that computer scientists have developed many of such models to solve very complicated tasks. And I'm wondering how, in what way those methods can be helpful to advance the frontier study in potential outcome models. Thank you.
Yeah, I don't really understand the questions. That's the problem. I think you think about these kind of machine learning models, and they are not using potential outcomes, or how should I interpret the question? I'm sorry.
Oh, okay. Sorry. Let me be simple. So what open questions do you think would be the most interesting in the potential outcome models?
What questions would be? Yeah. I mean, the potential outcome is just a way of setting up the problem for me. It makes with the potential outcomes, it's quite clear that what you are trying to identify. You put up counterfactual states, so that makes it possible to say, yeah, this is the potential outcome if you are not treated. This is the potential outcome if you are treated. But as soon as you start to have something like a continuous treatment, so you have multi-level treatments, then it starts to become very complicated. So there are these models that put up multi-level potential outcomes. And I think this is related perhaps also to Juni's question about that you have a continuous instrument. How should you then set up the potential outcome framework? For instance, you have a continuous treatment and you have a continuous instrument, like years of schooling is a treatment, and you have a continuous instrument for that. And how is the best way of viewing so that it's still very coherent what you are doing when you have a continuous treatment? And I guess, no, I haven't thought about it so much, but that is sort of a restriction in some way with the potential outcome, that it's very transparent and clear when you have just two stage. You have like the EV setup where you have 0-1 and you have a 0-1 treatment, then it is very coherent what you are doing, and that brings clarity to what you are doing. But it's not so coherent when you have more complex problems. And perhaps you cannot make it more coherent. You cannot make it. I don't know if you can sort of make it more coherent in this situation. So many times, sort of, when I do this with potential outcome and I have problem, even if I have, as I said to Joni, even if I have a continuous instrument, I make it discrete. I have a continuous instrument, and then I say, yeah, 1 if it's below the median, 0 if it's above the median or something like that, because then it's clear for me what I'm doing. I have when you say, I mean, I think with the potential, everything is there. It's the area of research, isn't that sort of more into with how to use machine learning tools in causal inference? Isn't that sort of the area where most research is done at the moment? How can we use sort of the large data set we have and machine learning tools to do causal inference? And I think it's very hard. You have papers by Susan Athy, Guido Imbens that are doing this kind of things. It has to do with the papers I've seen. It is more like dealing with this machine, the way to deal with big data and with the machine learning tools is to identify where the effect could be large, using the data before to then define. So it has to do with multi-significance testing as well. But at the moment, both in econometrics, especially in econometrics, I would say, they are trying to deal using these kind of machine learning tools and bring it into the causal framework. And I think many of them are using the potential outcome in describing what they are doing. But it's more of how to use the machine learning tools to design this quasi-experiment in some way. But I have not been dealing with that. But there is a lot of this kind of work at the moment. And what I've seen, the small thing I've seen, in econometrics, they are using the potential outcome when they do this kind of machine learning designs that I have seen. But no, yeah.
I also see some explorations in this direction, like the Susan Athy's work, as you just mentioned, her decision tree and random forest algorithm to use machine learning to learn a perfect or optimal binning to run a matching for the to estimate the average treatment effect. Yeah, thank you.
Yes, yeah, I think they are doing this kind of things, but I think they are not using these machine learning tools so much for estimation as to search for groups where they potentially, as I understand, you can estimate enormous, if you have big data, you can estimate enormous amount of effects. But you need to restrict your analysis to a certain amount of tests, because if you are doing too many tests, then you have no power at all. So you need to restrict the number of tests you are doing so that you can really sort of, if you are testing for 100 effects, well, then you cannot find anything because you have this multi-significance problem. So they are trying to restrict the number of tests they are doing where they believe that there could be any effect. It's a way of handling the multi-significance problem. That's how I understand what they are doing at the moment. But also with randomized experiment, as I understand. I thought so. Do you agree? Or
yeah.
No, this is a little bit things that I have not really been working with. Yes.
I understand. Yeah, everyone is exploring. I think no one has a perfect answer to this question, but I see a lot of computer scientists, a lot of statisticians are working to find a direction.
Pardon?
Yeah. Sorry. Yeah. I just want to echo you that I think a lot of people are exploring in this direction, but it seems there's no common sense that what is the correct direction that we should work on.
No.
Okay. Yeah. This is my first question, and I have a second question about the exogeneity that you just mentioned. That in many methods we require exogeneity. Like in IV, we hope the instrument variable should be exogenous, and in regression discontinuity, we hope the cutoff should be exogenous. I'm wondering, what if the exogenating assumption is not perfectly held? Like if a covariant, we believe it is exogenous, but actually it is not. How can we detect and quantify and correct this flaw?
No, I mean, you cannot. I mean, exogeneity is the same thing as unconfoundedness assumption used by Rubin. And the unconfoundedness assumption is more clear than this exogeneity assumption in some way, but it's the same. It's the same. It's basically the same exogeneity assumption and unconfoundedness. Exogeneity assumption could also be sort of, unconfoundedness has to do with the whole distribution is independent. With exogeneity, it may be that it's just independent of the mean, so mean independence in some way, not the whole distribution. So how to deal with it? What we have in regression discontinuity, for instance, is that there is a lot of these kind of sensitivity analysis using bunching. So we test whether this threshold really is what there should not be any possibility for the individuals to, the distribution around the threshold should be uniform, should be smooth. So we are using the data to test whether this assumption holds or not, or test, it's a sensitivity test. So what we don't want in the regression discontinuity design is that individuals can in some way cheat, or that the test it's possible for individuals to see if they can cross the threshold or not. So in that case, this exogeneity assumption in the regression discontinuity design doesn't hold. So what we are doing is that we are looking at using histograms. So if there is a clear distinction of individuals just on the other side of the threshold, you have more individuals on that side, on the other side, well then it's not exogenous. So the running variable is not exogenous. You can change the running variable yourself, or the administrator or something like that can manipulate the running variable. So in that case, you will see more individuals just to the other side of the threshold or not. And there is a lot of these kind of tests for that. How to handle this? I mean, if you have a treatment, if the instrument you are using is not exogenous, then there is no way of handling this, basically. That is so in the beginning you have a treatment. So you have a treatment that is sort of schooling, say. Economists started to see that perhaps individuals with high ability, they sort into more schooling. So that's an endogeneity problem. We solve this endogeneity problem by using an instrument. But if the instrument is not exogenous, well, then you need an instrument for the instrument. That would be the solution. To have have an instrument for the instrument. Yeah, that would be the solution. So what in the difference design, also in the regression discontinuity design, and also in the Ivy design, what we do is that we do sensitivity analysis if the data allows us to do that. So one very efficient way of testing the assumption is, of course, if you have data on individuals before the treatment, and you can run exactly the same regression as you are doing after the treatment, and you then see that, yeah, in this placebo regression, it's valid. It's valid. When then you are testing it under the null, and then you should not find any effect. So if you have data before, after for the same group of individuals, so that you can test the assumption by using data before, well, that's a validation of the exogeneity assumption. And today we have more and more data available, so you can do this kind of validation tests. And honestly, I mean, I believe that the Rubin-Korsel model with the matching is most often better than to do this kind of natural experiment when you have good data. So, and you can validate your assumption in this by running sensitivity analysis with the Rubin-Korsel model as well. So I'm a little bit disturbed about that economists don't trust this kind of Rubin-Korsel model. If you have really good data, I think the Rubin-Korsel model is a better way of doing it. The problem is that it's less sexy. It's less sexy. It's much more sexy to have a cool instrument to say, oh, I have this fantastic instrument. The economists, they like this kind of theoretical arguments that are finding these smart instruments, you see, finding these very smart designs with matching the Rubin-Korsel model, things like that. That's a little bit more hard. It's not this sexy theoretical ideas. It's more hard work, so no, especially since in Sweden we have extremely good register data. Why I think the assumptions of using the Rubin-Korsel model are really good, and we can test the assumption. I have a paper now that is, we published this design in the British Medical Journal. So we are estimating the effect of one cancer drug on another cancer drug using the Swedish register data. And when we published this design, we don't have the outcome data. So we put on the outcome data after we published the design. And now we have got the outcome data, but also outcome data that was measured before the individual got treatment. And then we can validate the design by estimating the effect on variables measured before they got the treatment. And in that case, there should not be any effect on these outcomes that was measured before treatment. And that's a validation of the design. So with longitudinal data, panel data, and you have a lot of data, the Rubin-Korsel model gives a lot of opportunities of having objective analysis, just because the design is not depending on the outcome variable. With all these, with many of the designs like IV and so on, you need to have the outcome variable basically when you do the design. So the advantage with the Rubin-Korsel model is that you can do the design without looking at the outcome data. And that is the most important thing. So when you are having a design and you are using the outcome data, well, then there is a risk that you do something wrong. It's highly risky that you are p-hacking and things like that. So that is a real danger with all empirical analysis. And by having this Rubin causal model, it's less risky that you are looking at the outcome when doing as part of the design. I hope you understand what. Yes.
Yeah.
I think all these natural experiments and things like that is really interesting and fun, and I have done quite cool studies myself, I think. But for some reason, if you have a lot of really good data, well, I think the Rubin causal model is in many ways better design.
I see. I can understand economics favors the smart design, smart identification, because it's simple, it's elegant, it's easy to understand. Yeah, but it's also it's difficult to find. So if we were not that lucky, and if we have enough data, we can always use Rubin's causal model to reach optimal or somewhat optimal solution.
Yes, exactly. So the risk is that instead of trying to answer relevant question, we try to find instruments that are cool for sub interested question that is of not so big interest, but we have a really nice design with this instrument. So we are sort of, we are not trying to deal with real value, real problems. Yes. I think so.
Thank you. Thank you so much. Thank you so much. That's very helpful. Thank you.
Yeah. Can I just have a comment related to that? Yeah.
Yes.
So I'm just thinking that if you have Rubin causal model like with matching that they can design, so you can actually easily deal with the multiple outcomes, right? Because
yes.
Yeah, whereas for the IV design, it's quite hard if you have multiple outcomes and you need to think, the IV should be exogenous and etc. for all those outcomes. It's really hard in this, especially in the big data era where you can collect a lot of outcomes.
No, I agree. I completely agree. That's a very relevant comment. Yes.
Yeah. Okay. Yeah. Thank you.
Okay. Thank you, Professor Huang, for the question, and thanks to Professor Zhang for the comments. And we have 2 more questions in the chat. Pear, I think you can also see it, but I will read it for you here. So from Yan Hongding, he or she asked, how do you think about the surge of RCTs in managerial practices and entrepreneurship studies those days?
Where is it? Perhaps
it starts with hi, Pear.
Okay. You can say, how do you think about the search in management and entrepreneur studies these days? Yeah, these days. Yeah, how do I think about it? yeah, it's a search. That's quite clear. It's a little bit scary when you think about how they are sort of manipulating you with all these experiments in social media and things like that. Yes. It's interesting what is going on, and I mean I have a previous PhD that is responsible for the research unit now at this company Spotify, and they are just running a lot of regressions of these experiments, and they come up with new methods as well. So in some way there is a methodological development going on in this field about also it's interesting in they can run these experiments over and over again at a very low cost, and also very small effects could be of importance for the profit. So there are so from a scientific point of view, I think this is interesting because suddenly there are new questions coming up that we have not been thinking about before. Very small effects could have huge effects on the profits because the experiments are so easy to run. And so I'm sort of, yeah, I think it's interesting from a methodological perspective, but from a personal perspective, I feel it feels a little bit not so nice to feel that you are taking part in experiments when you go into social medias and when you are using Spotify and other of these tools. But there are many new problems coming up, while research in doing experimental designs has, and I've been doing research in this area as well. So from a researcher's point of view, it's interesting. Yeah.
Okay, there is a second question about the potential joint point between data-driven machine learning method and economics. So
yeah,
would like to ask about your ideas about this topic.
Yes. I've talked about it to some extent, but machine learning, or when you want to, machine learnings are for predictions, really. When you want to estimate something causal, you need to have a design. It's quite clear. So I talked with, I forgot this professor's name, but it's related to that. You can use this kind of, and it is used in econometrics nowadays, this kind of machine learning tools, but it's part of the design. You cannot use the machine learning programs to estimate causal effects. That is not possible. You need to have a clear understanding of the subject matters to estimate causal effect, and you need to have a clear design. You can use the machine learning tools to some extent, as I understand now. For instance, the paper by Susan Athey and Imbens to use that for the design. The same thing, if you can use this kind of machine learning tools also in the Rubin causal model to find matched individuals and to find weights, and that's used quite a lot. I know Donna Rubin really don't like this kind of automatic procedures. I think I'm sort of in between. I think sometimes it can be very useful to have this, but you need to pay attention to what you are doing. You cannot let the machines finding the matches and the weights and without really thinking about analyzing the data after you have used this kind of machine learning tools to find matches used in the Rubin causal model. You really need to look at the data and pay attention to it so it makes sense in the end of the day. So I think that it can improve the possibilities of using the Rubin causal model, because if you really would like to find the way, use subjective knowledge in finding the matching, that can be quite tedious and really a lot of work. So if you have procedures like entropy balancing by Heinmüller, who is in political science originally, I think that could be quite useful. But one need it's no, you need to understand what you are doing. That is quite clear.
Okay. Is there any other questions from the audience? I think we have covered a lot of topics today and also got a lot of feedback from people from different research area, like politics, statistics, economics, and management. So I enjoy this lecture and all these feedback discussions a lot. And I hope the whole audience also enjoy this. And because we didn't finish the lecture today, so I'm guessing, Perry, if you want to continue the remaining part next week at the same time, and we will also have the guests here, and we can discuss. We have longer time so that we can discuss this.
Yeah.
What do you say?
Yeah, the difference. I think it's good to know about the difference in difference. No, it was a little bit tedious. I know that, but I can do that if there is an interest. But my lecture was not so good. I think. But if
I
there
think
is
it's good.
if there is an interest, I can do that. Yes.
Yeah. I think we all want to hear more about the following content about the difference in difference thing. And okay, so it has already been like almost 3 hours for today.
Yeah.
And I guess we may stop here, and next week we can continue on this.
Okay.
Okay, thank you. Thanks again for your great lecture, and thanks for all the guests that we invited and the whole audience. And we welcome you the same time next week to continue the lecture here.
The majority of the papers in labor economics, health economics, and so on are based on this kind of ideas with quasi-experiments and quasi-experimental design. They are all now framed in the Rubin causal model. So that was, so the Rubin causal model is also a quasi-experimental design. But I did not talk about the Rubin causal model because you have had lectures by Donna Rubin before. So I hope you are informed about what is the Rubin causal model. The intention was to cover then the main natural experiment or quasi-experimental approaches in economics, which is the instrumental variables method, the regression discontinuity method, the difference in difference, and the synthetic control. And all I did was to talk about the instrumental variables, solution, history, and how it's nowadays interpreted through the lens of Imbens and Angrist, Imbens and Rubin paper. And that was sort of the reason why Guido Imbens and Joshua Angrist received the Nobel Prize, was that they sort of combined the Rubin causal model with the framework we have in econometrics, framing it in this original way with the simultaneous equation models, and combined it with the Rubin causal model, which add transparency into how we should interpret results using the instrumental variables method. So that was last time, and so we stopped here last time where I summarized the things from the late. Yeah, so that's where I stopped. And now the regression discontinuity design then. This dates back almost half a century to the paper by Tisthwaite and Campbell, 1960. They were studying the effects of merit awards using this design, but it was rediscovered by the economist van der Klauw in 1997. I just talked with Donna Rubin about this. We had a discussion in my lectures Thursday, so it's a little bit interesting perhaps. So Donna Rubin never thought about this as a design. The reason is that when he read the paper by Tisthwaite and Campbell from 1960 early on, it was all framed like an estimator, like a regression estimator, and that's not a design. But when I was lecturing, giving a lecture about this on Thursday, I think he started to understand, yeah, now perhaps one can think about this as being a design. A design means that you are thinking about the data on which units you can identify something. So now I think he's more open-minded towards that. And it's interesting to note also that Donna Rubin wrote a paper on a regression discontinuity design that is not mentioned in the literature, basically. I don't know how many citations there is from the paper, but I found this when I was working on this Nobel Prize in economics, and it's very nicely written, because it's basically written as a design. And when I mentioned this to Donna Ruben, it was like he almost forgot that he wrote that paper, so he don't remember. But he did not introduce at that time, when he wrote this paper on regression discontinuity design, he didn't use the potential outcome framework. He used the observed outcome, like Twistlethwaite and Campbell writing it. If he had used the potential outcome framework writing that, well, then I think he would have been credited for making this into the design we are now using in economics. That is my interpretation. The paper by Donna Ruben, if you like to read about it, it's interesting because he's suggesting a matching estimator rather than a regression estimator that Twistlethwaite and Campbell suggested in this paper from 1960. Anyway, so the regression discontinuity exploit discontinuities in most often it's a policy assignment. For example, there might be an age threshold at which one becomes eligible for study grants, or an income threshold at which one becomes eligible for financial aid, something like that. So we can think about it like, if we look at this figure here, perhaps I should make it a little bit bigger. Yeah, you see here, you have the data, and then you have a threshold here, which is denoted with X. I will use C later on. And then at this threshold, there is a jump in the outcome variable, sort of. So then what this regression discontinuity estimator is trying to estimate the effect at this jump. This is sort of the discontinuity. So this could be age, as I said before, and it could also be sort of income or something like that. So you have this variable age, which I will denote set in what follows, which is the running variable or forcing variable. And then you have a threshold here that we are using in identifying treatment effects. Yeah. Okay. So, for example, there might be an age threshold. So this means that you have age as this on this x-axis at which one become eligible for study grants, or an income threshold. So you have an income variable. So you have an income and you have a threshold when you become eligible for financial aids. So the general idea is to assume that the units of the different size of this discontinuity are similar. The treatment status differs because of the institutional setup, and differences in outcomes can be attributed to the different treatment status that we saw on these pictures. So on both sides of this threshold, you assume that individuals close to this threshold are equal. And that's, of course, an assumption that you in some way need to validate. You need to validate it by describing the rules you are using for this threshold. And you are also trying to validate this by looking at data. I will consider the short design, where the assignment follows a deterministic rule, and the fuzzy design, where the probability of being treated is discontinuous at a known point. Under fairly weak assumptions, this consistently estimates a local treatment effect around the cutoff. So note, we are not talking about an average treatment effect that you talk about in a randomized experiment. We say it's a local treatment effect. The problem may be from this type of analysis, if the assumptions are false or are correct, is how to interpret this effect. How can we generalize from this type of design to something broader than just from this specific study? So as before, there are two potential outcomes. You have yi0 and y1 I1. So you have two potential outcomes exactly in the same way as you have in the Rubin causal model or in an observational study, or when you have a randomized experiments. This is how things are set up nowadays using the potential outcome framework. There is also a single covariate set, and this is then the running variable, okay, or forcing variable that affects the treatment W. So we are interested in the treatment effect of W as we were interested in the treatment effect in the IV setting. But now set is not an instrument, it's a forcing or running variable. So that's how the two designs distinguish themselves from each other. Set is not an instrument, it's a forcing or running variable. As before, we observe W, we observe set, and yi, the observed outcome, which can be written like this. Under the stable unit treatment value assumption that I was talking about before, that is, the individual's treatment should not affect the potential outcomes in per se. So the potential outcome are treated as fixed. We have the same treatment for everyone. So we have one definition of a treatment, and then you need the stable unit treatment value assumption for the observed y to be equal to the potential outcome if not treated for those that are not treated, and the potential outcome for of being treated for the treated. And I think this is the strength of the regression discontinuity design. I think this Sutwa assumptions most likely will hold in most settings. Yeah. Assumption one is that the treatment is given is equal to 1 when this running or forcing variable is bigger than this threshold C, and Wi is equal to 0 if this running variable is less than this treatment C. So all individuals where set I is bigger than C receives the treatment, and all individuals where set I is less than C do not receive the treatment. Wi is a deterministic and discontinuous function of set I. It's a deterministic, meaning it's very far from the randomized experiment. In the randomized experiment, if you have talked about that, or the way I talked about it, was that the variation in the treatment in the stochastic element, the only stochastic element is the treatment assignment. And here Wi is deterministic, not random. So that means it's very distinct from the randomized experiment. Assumption 2, this is the critical assumption for the RD, both the short and fuzzy designs. And this is that the underlying conditional mean functions should be continuous at the threshold. So the potential outcome, the expected value of the potential outcomes under treatment or under the control should be continuous at the threshold. Cannot be any discontinuities around this. All needs to be driven by the threshold. The effect needs to be driven by the threshold. So there cannot be any non-linearities of the mean function at the threshold. That's the bottom line. Yeah, perhaps I can illustrate that. We will come back to this. But this is from Angrist and Pitschke 2009. So this is the rounding variables. You have a discrete jump here at the outcome. Here you have, here they illustrate something where you have a nonlinearity at the threshold. So this is just nonlinearities in the outcome variable at the threshold. So this would not validate the assumption 2. So that's the bottom line. Since Wi is a deterministic function of set I, unconfoundedness or independence holds. So unconfoundedness means that the expected value of the potential outcome under no treatment, given that you are treated, is equal to the expected value of the potential outcome under no treatment for the non-treated. And this means that you can estimate this for the treated using the data for the non-treated, since this is observed. So this is observed in the data. And the same way when it comes to the expected value of the potential outcome under treatment for the non-treated is equal to the expected value of the potential outcome under treatment for the treated, which is observed in the data. So okay. However, the overlap conditions, that is the probability given the running variable should be between 0 or 1, does not hold at all. So I don't know, we never talked about the Rubin-Causal model, but the Rubin-Causal model is that for you to identify a treatment effect with observable covariates, the first assumption in the Rubin-Causal model is the Sutwa assumption. The values of yi1 and yi0 for a given individual are not affected by the values taken by wi. We talked about that. Assumption B is the unconfoundedness assumption, meaning that the probability to be treated given xi and yi is independent of the potential outcomes. So this holds. We talked about that. So this is in the economics literature called the conditional independence assumption. So that would hold. But then you have the common support assumption as well, and that is that everyone with the same X should have the possibility to be treated or not, and this is called the common support assumption. And assumption B and C are called the strong ignorability of the treatment assignment assumption. This is not valid in the regression discontinuity design. Okay, so this is the distinction because Wi is either one, the probability to be treated is either 1 or 0. So it is not strongly ignorable to any stretch of imagination. Therefore, we cannot, unless we are willing to assume a constant treatment effect or a very strong functional form assumption, estimate an average treatment effect. So if we assume that we have the same treatment effects for all individuals, that we have a constant treatment effect, well, then we are also estimating the average treatment effect. But most likely that is not the case, so that is a very strong assumption. With heterogeneous treatment effect, we typically have that this estimand of interest, delta C, that is defined here, differs from the average treatment effect, that is the treatment effect for a well-defined population. Okay, so this estimand is the expected value of yi1 minus yi0, given that the running variable is at the threshold. And this is the expected value of y1 at the threshold value C, and this is the expected value of yi0 at the threshold C. And both this can be estimated given that we have data close enough to the threshold. So this is the average treatment effect for those at the margin of receiving the treatment. However, because this is a little bit limited, it's at the margin of those receiving the treatment. Delta C is identified with only one key assumption, that is that the expected value of the potential outcomes given the running variable are continuous at this point C. The interest on this estimand delta C depends on the application. So generally, we sacrifice external validity for internal validity. And there are papers out there, if you know, if you want to read more on this, that try to find ways of extrapolating from a regression discontinuity design to a larger population. So there exist papers to do that, how to do it, and so on. So we can estimate these two means separately by only calculating the means for those individuals in the small neighborhood around the cutoff. The argument is that these will be similar as in a randomized experiment at the cutoff point because they have very similar set values. Hence, delta C can be estimated as the mean around the threshold to the right minus the mean to the thresholds to the left. So, yeah. This is the number of individuals with set I values in the interval C to the C plus delta and C minus 1 delta C. As you saw here, we are summing over the individuals in this area between C and C plus delta. And in this area, we take the individuals in the area C minus delta to C. And then we divide it with the number of individuals in these areas. In practice, there is a trade-off between bias and efficiency. If we have very few individuals, we take if the individuals just close to the threshold, like this figure we have here. So if we just take these individuals here very close to the threshold, like 4 individuals, and these 4 individuals, well, then there will be a small bias. But as we will talk about, perhaps we can use the functional form, how this running variable is affecting the or correlated with the outcome. Then we can use all data here to estimate the treatment effect. So few individuals, little bias, but large variance, because variance of an estimator that takes all that are only using four individuals to estimate the mean for the being in the control group, and 4 individuals that are in the treatment group will have very large variance, of course. Okay, so there is a trade-off between bias and efficiency. Few individuals close to the threshold, low efficiency and small bias. An alternative or complement is that of using ordinary least square based on this function. So you have the observed value of yi is equal to the expected value of yi0 at the threshold, that is defined as beta naught in this line below, in the second line. Then you have delta C, which is the estimate of threshold, that is the treatment effect at the margin, that is people at this threshold. Then you have a regression line to the left of the threshold, and you have a regression line to the right of the threshold. So you put this up, so then the estimate of delta C is the jump in the linear regression at set is equal to C. So looking at this, well, with this type of data, well, you have one regression line here, this is beta 1. You have another regression line here, this is beta 2. And in this example, beta 1 and beta 2 would be similar, very similar. When you have a similar regression line on both sides, this is the original application of Twist, Wattle, and Campbell from 1960. That's how they put it down. So they simply estimated, if you remove this second part, they estimated this. And that's why Donna Rubin is sort of critical of this. This is not a design, it's simply an estimated. So they control for the regression like this, removing this threshold. So they just included this running variable in the regression model, and then they estimate something at the threshold. Since Wi is completely determined by set, we have that the expected value of the error term in this regression model is equal to is just conditional set. So it's independent of the treatment. And this means that we have an unbiased estimator, given that the model is correct in some way. So we need to model set I correctly. So if this is correctly specified, well, then we can get a consistent estimate of delta C using all data. But if we don't believe we can capture everything in the set I in the regression model, well, then we get some biased estimator, of course. And that's why we need to be careful and perhaps just estimate things local and not use the whole data set. Yeah, beta 2 is equal to 0 if linearity is the same on both sides of C. So in this model, you could test for it if you like. To estimate this local treatment effect, we could either use the full data set or limited data set based on some procedures and estimate equation 5 using local linear regression. So there are ways of doing that. So instead of using the whole data set, going back to this figure here, we could say that we are just using these individuals here to estimate a linear regression on this set, just like this. We just take this, we'll estimate the linear regression. And if you see here, this is also a valid regression discontinuity design. But here you have like a polynomial on both sides, and the polynomials look different on both sides of this threshold. If you were using this linear regression model with just the forcing variable or running variables linearly, then it would be perhaps relevant if we are limiting the regression estimated to this part of the data on this side. Yeah, if you are limiting to this 15 observations here and 15 observations here, the linear regression model would be quite valid. But if we use all the data, then we would get biased estimators of the trash of this shift here. So functional form assumptions on the running or forcing variable is important if you are using data far away from the threshold when doing the analysis. Okay. So there is a trade-off between bias and imprecision of the estimate of delta C, also using ordinary least square. So when we use the ordinary least square, we can choose delta, that is this around this threshold sort of set, either by experiments by different delta, small, well then we have reduced bias and decreased precision. There are many procedures out there now. So this is one procedure. Use a database method which gives an optimal bandwidth choice. So you can see at Invens and Lemieux, 2008. But there are new approaches popping up all the time of doing this kind of estimation. The regression discontinuity design has become very, very popular in economics. The reason is that you can present your results graphically. And if you can present your results graphically, that means it gets more convincing for the people you are presenting it for, if you can present. And in some way, this way of presenting things so that it's convincingly has started to be an artwork almost rather than science. I'm a little bit skeptical of it, but this is just how it is done. So bias can also be reduced by adding higher order polynomials of these running variables to equation 5, then interacted with W. And that is, of course, if you have data that look like something like this, where the second order polynomial on the left-hand side and the second order polynomial on the right-hand side would mean that you could sort of estimate the treatment effect validly using this shift that we have presented on the regression, on this regression model, so this shift. So here you have delta C, but then you have set I minus C, and then you have beta. Yeah, you have that, but then you also have a second order interaction on this, and then you have a second order interaction on this. And what people in economics often do is that they have these regression models. They try out sort of different polynomials, first order, second order, third order, fourth order, and so on. And then they see, sort of eyeballing, how stable the estimates are for different model specifications. And also combined with different thresholds, deltas. How far can you sort of, how much can you limit the amount of data using a delta that is by increasing delta to some extent. So it is some artwork going on, and that one can be a little bit skeptical of when interpreting the statistical significance, because it's a lot of modeling and you are modeling things using the outcome variable to do that. So it is, from an inference perspective, could be a little bit problematic. One can also add regressors to the equation 5, not interacted with the treatment variable. So you can remove increased precision by adding regressors. So if you add regressors to this model, well, then the variance of epsilon I most likely will be reduced. So that would increase precision. So if the covariates are important in describing the outcome variable, well, then you get more precise estimates by adding covariates. Okay, so the validity of RD turns on our willingness to extrapolate across covariate values, at least in the neighborhood of the discontinuity. Yes. This distinguishes the short RD from other regression control strategies, which are based on the treatment control comparison conditional on covariates values when there is some overlap. So this is sort of, I talked about the Rubin causal model, sort of. Okay, this I have taken from Angrist and Pitschke, and I just sort of, it's an illustration that I have been using now. So this is an example where you don't have a regression discontinuity design. It is rather non-linearities in the data. So in order for you to use the RD design, you need to describe the institutions. Why can we have this type of short RD design? You need to validate that for the reader by presenting institutional details. You read very clear in describing the institutional details. The fact that you have some kind of idea about the threshold and that you plot the data is not enough. So the fuzzy RD design exploit discontinuities in the probability or expected value of treatment conditional on covariates. The discontinuity in this running variable becomes an instrumental variable for the treatment status W instead of a deterministic switching treatment on or off. So this means that you are using this design, but then in the end of the day, you are estimating things using the instrumental variables estimator. And in general, I have never seen anything else. They are using the two-stage least square estimator that we talked about last time when discussing the IV setup. The two-stage least square estimator was that you first estimated how the instrument, in this case, you have the instrument is the running variable, affects the treatment, and then you estimate how the predicted value of the treatment are affecting the outcome. So that we talked about that. So that is two-stage least square estimator. We estimate things using two ordinary least square estimator, the first step, and then by plugging in the predicted value from the first step, you estimate it using ordinary least square in the second step. And then you need to take into consideration how you are estimating the standard errors after that. Okay, set still determines W, but now in a non-deterministic way. So that's why I say, yeah, here you have the first step. You're estimating how the running variable determines W in a stochastic way. In the fuzzy RD design, the probability of treatment changes discontinuously at this threshold. So define the propensity score, which was defined by Donna Rubin and Paul Rosenbaum. I hope you discussed that when talking about this with when Don was giving his talk. That is, the probability to be treated is a function of this running variable and its F set. This is the two designs. So the short design means that the probability to be treated is 0 for everyone up to this threshold, which is S bar in this figure taken from Cameron and Trivedi, but it's C in my notes. And then it goes up directly to 1 here for all other, for individuals to the right of the threshold. The fuzzy regression discontinuity design, the probability to be treated as a function of this propensity score is gradually increasing up to the threshold. And then there is this jump. And it's this jump that we are using to estimate things using the two-stage least square estimator. And then it continues to increase up to a certain level. So this is the fuzzy RD design, in contrast to the sharp RD design, where the probability is equal to 0 up to the threshold and 1 after the threshold. In addition to assumption 2 for the sharp regression discontinuity design, if you remember, it was that these mean value functions are equal or continuous at the threshold. So this was assumption 2, the critical, that the conditional mean of the running variable is continuous at the threshold. So in addition to this assumption, we have assumption 1, which says that the propensity score is discontinuous at this threshold C. So there is a discrete jump in the probability of a treatment at the cutoff, illustrated by this figure. So this is the assumption. You have this jump in the threshold. This means that the probability of treatment differs when set goes from C from below compared to when set goes to C from above. So short RD selection depends on observables, that is the set variables. The fuzzy RD design, the selection depends on observables and unobservables. So we use IV in combination with RD. So I talked about that already. So sharp selection depends on observables. So that's the selection of observables estimated. Exactly like the Rubin-Causal model, but the Rubin-Causal model is based on the randomized experiments where we have the ignorability assumptions, meaning that we are replicating a randomized experiment. Here, we have no common support. All individuals to one side is treated and all other individuals on the other side is not treated. The fuzzy RD depends on observables and unobservables. So this is an IV estimate. It can be shown that it's sufficient to assume that the treatment variable is independent of the treatment effect conditional on the running variable. So yeah, we put this up when we were discussing the late estimator last time, if you remember, these kind of assumptions, but it's enough to just say that the treatment effect would be independent of the treatment assignment given the running variable. So this is a weaker assumption than to assume that the treatment is independent of Y1 and Y0 given set time. It's a weaker assumption. So this is sufficient. Then it can be shown that this estimand delta C is equal to the outcome mean to the right of the threshold minus the outcome mean to the left of the threshold divided by the propensity score to the right of the threshold minus the propensity score to the left of the threshold. Okay. So this in the short design, this was what we had in the short design. We didn't need to divide by this shift because just to give an illustration, in the short design, we go from 0 to 1 directly. Now we only go from this to this. So we take this F plus is here, and then this is F minus, FC minus in this graph. So since we don't go from 0 to 1, we normalize the outcome changes by using the percentage that really have that really change the status due to this threshold. So in the short design, we need only to estimate this means to the right minus the means to the left for those at the threshold. Now we need to normalize the effect because not everyone is treated to the right of the threshold, and not only and that the individuals just to the left of the threshold, not everyone is not treated because some are also treated before. Okay. I think I said all this. So n plus z goes from above, from below, from above, from below. Delta C is identified if M and F are identified in the neighborhood of C, and if this F plus C is different from F minus C. So you see, this is if there is no jump. If there is no jump here, well, then we cannot identify anything. Then we cannot identify anything. Okay, and this is the Wald estimator in the IV setting that we talked about the last time. Okay, I have a question. Oh, this was a long question. I can answer this question perhaps later on. This was too long. Donuts test. Oh, okay. Yeah, we can. Yeah. This was a very hard question to talk about now. I will try to end with discussing this question. I hope you are following me here. Okay, we can then use the estimator where we simply plug in an estimates for the mean to the right of this threshold with the mean to the left of the threshold and with an estimator of the propensity score, where all four quantities can be estimated using local linear regression like LOES, splines, and things like that. As shown by Van der Klauw 2001, this estimator is numerically equivalent to an IV estimate from the regression model. So this was suggested by Van der Klauw in 1998 paper, but then there is this follow-up paper by Van der Klauw, Petra Todd, and I forgot the third author, where they say that, yeah, you can get a numerically equivalent estimator by using the two-stage least square estimator. So here, note that this is the Wald estimator. If you remember, we talked about that. I can just show the similarities. History models. Yeah, here. This is the Wald estimator. So we first estimate 3 and 4 with ordinary least square. So you estimate this model. This is the first stage. Then you estimate the reduced form where you include the instrument on the outcome variable. And then you take alpha 1 divided by delta 1. And this is called the Wold estimator. And with no covariates or nothing like this is equivalent with the two-stage least square estimator. So what you can see is sort of, since the ordinary least square estimator is equal to the mean differences, this is the Wold estimator. So you estimate the means to the right and to the left of the threshold using individuals, and then you estimate the changes in the probability to be treated at the threshold. So this is the Wold, and that's why I have the Wold fuzzy regression discontinuity design. But then they show that, yeah, you can estimate everything on the fly using the two-stage least square estimator. The problem now with this setup is that you have this endogenous variable, the treatment, but then you also need to adjust for the fact that it could be non-linearities in this forcing variable set. So you have two endogenous variables. You have the treatment, and then you have this sort of how the treatment varies with the running variable. So you have two endogenous variables. So you need two instruments. So you use this as an instrument for the treatment variable, and then you use this that where set crosses the threshold C, interacted with set I minus C for this endogenous variable. So this means that you need to estimate this as a first step. So you have two endogenous variables and you have two instruments, and that's how you estimate this using the two-stage least square estimate. Any other question than these very long questions on the regression discontinuity design? Otherwise, I go over to the difference in difference estimation. Question is if I should read this, perhaps try to answer it in some way. Okay, so I read it. I do that now. Dear professor, in a paper using geographical sharp RD, I conducted a donut test in which we dropped the observations household close to the cutoff to reduce the concern that there is a possibility of sorting adopted by the households. Seems very good. No, I need to make this. In the paper using an icon donut test in which we drop the observations household close to the cutoff to reduce the concern that there is a possibility of sorting adopted by the household. And it results is very close to the one using non-donut baseline estimate. A reviewer questioned this strategy and said that the RD is based on a local average effect. Yes. So donut test is nonsensical. But I saw a few papers in top 5 using the donut test as well. How should I reply this reviewer? Yes. Yeah, sometimes, I mean, the reviewer is right. He is right to some extent. He is right. But people that have a reputation, that are publishing already in top 5 journals, they are not reviewed to the same extent than people that don't have the same reputation and that comes from other universities. So we that are not at the top 5 or not at the US universities, I think we are scrutinized more. I mean, so think about it like this. What he says is that you have so much heterogeneity. So if you just remove some of the individuals, you could get completely different estimates. But this means that if you assume that under the assumption of homogeneous treatment effects, I'm just talking now, I have no idea how. But if you have homogeneous treatment effects, then the test is valid, of course. If you have very different treatment effects for all individuals, then it's nonsensical. So you need to assume some way that you have some heterogeneity, but you should be able to, I mean, what this person is saying in some sense is that you can estimate a treatment effect, but you can never ever generalize from this to something else. That's basically what this is saying. And that doesn't really make any sense either. This is one way of testing it. So the question is if you could do something complementary, some other form of test to sort of please this reviewer, perhaps. No, I mean, this area with the RD design is not really my, I have not done any RD design myself. I'm teaching it. I have had students doing it, so I have some experiment, but I'm a little bit, this is a hard question. It's very, I think it's one way of responding to it is to try to say that, yeah, you are right in some way, but this is implemented, others have implemented it in the literature, and of course, if we believe that we have so much heterogeneity that we cannot generalize from this at all, yeah, no, I should stop talking because I don't know. I don't know. I hope this is a hard problem, and I should perhaps read the paper that you have been doing, try to help you in that way with some more advice, but not at this lecture, I think. In some way, the referee is correct, and it's not a very perhaps fair comment in another way. That's how I think about it. You do what you can do. Yeah. Okay. So let's continue with the difference in difference. What have I happened? Why can't I? Oh, what happened now? Okay. So difference in difference. Often used for, but not limited to policy analysis. I will show you one other way of doing difference in difference than perhaps you have seen before. Simplest case, 2 time periods and 2 groups, treatment and control. That is, you have 2 groups and you have a treatment and controls. That's the very simplest case. In the second period, there is a policy intervention affecting the treatment group, but not the control group. No treatment in the first period, not random assignment into treatment and control, and pioneered by Johansson, 1855, who studied the cholera epidemic in London. The Johansson paper, 1855, was this, that there was, he had a theoretical idea that cholera was transmitted by contaminated drinking waters. 2 water companies, the Southwark and Vauxhall Company and the Lambeth Company. In 1849, both companies took the water from the dirty River Thames. In 1852, Lambeth Company moved this water work upriver, relatively free from sewage. So this is a form of experiment. The individual did not freely choose the water supply, but not randomly assigned. The companies served different districts why we denote it a natural experiment. So in this case, I mean, you have people, and I believe this is fair to say that, yeah, natural experiment means it's only the nature that you are using. For instance, birth orders, twins, siblings, and something like that is a natural experiment. Here it is humans, it's a policy in some way. Lambert Company moved this waterwork up river. The reason for it, we don't know, but it's a policy change, and still people are using this as calling this a natural experiment. Some people think one should only use natural experiments when you are using the nature. Like, for instance, I have a paper where we use inversion episodes to study the effect of pollution on health. Well, then we are using inversion episodes as a change in the pollution level, so it's something that comes from the nature. And some people have talked about this as natural experiments. Yes. So then they study sort of what happens after that they move the waterwork upstreams by Lambert Company using the Southwark and Vauxhall Company as a comparison and looked at differences in mortality. So the outcome is to look at mortality after moving the waterwork upstreams. Is it reduced by the Lambert Company, the people being served by Lambert Company, in contrast to the company served by the Southwark and Vauxhall Company? So one reason that there could be problems is that the mortality rate could differ for other reasons than just moving the waterworks. Well, the customers served by the Lambert Company could be richer, for instance, than the people served by the Southwark and Vauxhall Company. Other demographic things could also differ. Additionally, there could be time trends in mortality rates. So there could be sort of reduced mortality rates over time, or there could be increased mortality rates over time for different reasons. Some other famous examples are raise of minimum wages in New Jersey. This we talked about in the Nobel Prize. If you read something about sort of motivating the price for David Card, this was a very famous example that changed the literature in labor economics. So the motivation for the Nobel Prize in economics was, we talked a lot about this raise of minimum wages in New Jersey. So they used sort of, David Card and Ashenfelter used the fact that you change the minimum wages in New Jersey, and then they compared sort of the employment rates and the wages in fast food restaurants. I will not go into that details. The unexpected immigration flow to Cuba is another example, and I will talk about this later on. I will go back to that. And these are both papers by David Card, and they transform the labor economics. That's quite clear. So the general difference in different setup is like this. Let group A and B be the let group A be the control group, not implementing the reform, and let group B be the treatment group implementing the reform in 2 time periods, 1 and 2. Then the effect of the reform can be estimated as this. Just the differences in time period 2. This is with the difference in time period 1 in the treated group, minus the differences in time period 2, minus the difference in time period 2 and 1 for the untreated group. So that's why you call it difference in difference. You are controlling for potential time trends in mortality rates when it comes to this cholera epidemic. So you have time trends in mortality is controlled for. So in this company, Lambert company, you are studying the mortality rate in the second time period with the first time period, that is before they move the waterwork. And then there could be trends in this. So we are controlling the time trends using the other company's mortality rates. Okay. And the alternative approach is to estimate an interaction or factor model, that is to estimate this regression model. And this is how economists now are mainly doing it. So here in this setup, dB takes value 1 for the population affected by the policy. And dB is equal to 0 for the other group, that is this other waterwork company. And D2 is equal to 1 for time period 2. So this is the parameter of interest, the time to interacted with the treatment group. So beta 3 in this regression model is exactly equal to the difference in difference estimated that we have here. If the policy were implemented in a random fashion, we could just use the differences in mortality rate for the Vauxhall company in time period 2 with the mortality rate in the second period for the Lambert company. Okay. But it could be that the customers served by the Lambert company and the Vauxhall companies were different. So we need to in some way take this into consideration by normalizing with the time period 1 mortality rate of the companies, customers that were served by the two companies. By instead relying on the difference in difference estimate, we can allow for some form of endogenous adoption of the new treatment. And this is a little bit vague of me, but what I mean with this is simply that, yeah, as I said here, mortality rate could differ for other reasons, socioeconomic and demographic. Yeah, the two companies could be serving different types of populations. So the Vauxhall company could be serving people with higher income or something like that. So there is some correlation between sort of variables correlated with mortality rates. That's what I mean. But by taking the differences in differences, we can control for this form of endogeneity. Adding covariates to the regression equation is straightforward if they are not affected by the policy or treatment. So if you have a situation like this, well, then you can add covariates by that. But the covariates should be, in general, measured before the treatment, before the change in policy. Otherwise, it can lead to false inference. A further advantage with the regression framework is that it's easy to be used with repeated cross-section data in G groups observed in T time periods and or for panel data of individuals I. So if we have individual observations, so we observe individual over time, well, then it's easy to estimate this just using this kind of regression models. And this is the setup with the many groups. So with many groups, you control for the time fixed effects, you control for the group fixed effect. In this case, we have capital G groups. And then you have this difference in difference estimated that is equal to 1 if an individual I is treated at time period T. Yeah. So we treated, I mean, pressing treated, so this is how you would put it up. So you have individual I, G, T, and in this case you have I measured at mg. So you have mg individuals and in each group, and this is a panel data setting, so it's very flexible. So you can use individual data, but many times when you see this type of estimators from US, for instance, we are using group averages to do the estimation. But this is a very flexible way of doing it. The main difference in difference assumption is that the outcome of the treated after the treatment or reform, that is the counterfactual state, would not have been affected if not treated. This means that the differences in the expected value of the treated group, okay, the expected change in the outcome of the treatment groups, given that they were not treated, would have been equal to the differences in the control group or comparison group. So this is in this language that we are using in economics, denoted as the parallel trend assumption. So the parallel trend assumption. So yeah, if the reform is exogenous, this assumption may be plausible. If a policy change is implemented because of changes in Y in the policy regions, the assumption may be less plausible. So if the policy is a consequence of changes in Y, well, then it's hard to publish the paper in a good journal, I would say. If you have this situation and you have something that is highly policy relevant, well, then one solution is to condition on pre-policy changes in mean Y. So it is possible, but then the analysis is based on quite strong assumptions, so it may be hard to publish in the best journals. But of course, it depends on how important the question is. With many observations of the outcome before the reform, the assumption is tested by observing that the trends in outcomes of the group are parallel before the reform. And this is an illustration from a paper by me and Nikolai Angelov and Erika Lindahl in the Journal of Labor Economics. It is a difference in difference setting, but in a very non-traditional difference in difference setting, and are now in economics rather called timing of events study. I think they use it like this. But this is the income years for women. This is for men, and this is couples in the data from the Swedish register data. So we are combining couples that have the children at time period here. Here they receive a child together. So this is the fathers and this is the mothers of the child, and this is the income. And here we have income data 10 years before they have a child. And what we see is that the income development are exactly parallel before they have a child together. After that, there is a dramatic change in the income for the mothers, and then you start to see similar trends as before for the mothers, but a slower increase in the incomes, and this is for the fathers. But the important thing here for us was to show that the trends were similar for the mothers and fathers. And when you do something like this, with the difference in different setting, you have an assumption that can be quite strong, and that's an additive separable assumption. So for the analysis, it would have been even better if these two income trends were very similar before they have children. Now there is a gap. So this means that in order to do the difference in difference setup that we are doing here, we need to assume that the functional form is in some way correct, additive separable. So the question then is, what does the difference in difference estimate? It's not so clear, perhaps. We have discussed sort of the late estimator using the IV setup. We say that, yeah, if we have heterogeneous treatment effect, we are estimating the compliant treatment effect or the local average treatment effect. In the regression discontinuity design, we say that, yeah, we are not estimating the average treatment effect. We are estimating a local treatment effect. We don't really know what we are estimating. If you can assume more homogeneous treatment effects, well, then we have something that is of highly policy value. If you have a lot of heterogeneous treatment effects, well, perhaps you cannot even generalize from this study to something that is of relevance. Angrist and Kruger, 1999, seems to be the first framing the difference in difference strategy using the potential outcome. And as you have seen, putting things up using the potential outcome framework means that it's possible to interpret the parameters in a way than rather a parameter in a regression model. As an example, they used the influential study of Card, who used a large unexpected influx of Cuban immigrants to Miami, the Mariel boat lift, to estimate how the labor market outcomes among natives are affected by this immigration using the difference in difference strategy. The Mariel boat lift increased the Miami labor force by a staggering 7% between May and September 1980. So that is a huge change. Angrist and Kruger, 1999, let I0 be I's employment status in the absence of immigration. And they let Y1 be the employment status if the Mariel immigrants come from I's city. Come to I's city. Yeah. So the unemployment rate in city C in year T is equal to the expected value yi 0, and then you're conditioning on C and T with no immigration wave, and the expected value y1 C and T if there is an immigration wave. Okay, so you see, we first define the individual potential outcome. But now, since we are measuring things as unemployment, you can either be unemployed or not. It's not so relevant. Perhaps it's not even, I mean, it's possible, but you have here unemployed or not. So why for the individual observation, yi0 is either 1 or 0. And this is also either 1 and 0. Takes only, it's a binary variable, unemployed or not. So the unemployment rate is equal to the expected value of yi0 for the population living in city C at year T. So this is the unemployment rate. It's simply the expected value of these potential outcomes. With no immigration wave, and this is the unemployment rate with the immigration wave. In practice, we know that the Mariel immigration happened in Miami in 1980. So the only value of this outcome with an immigration wave is for Miami in T is equal to 1980. There is a lot of possibilities of estimating the counterfactual immigration at this time, but there is only one observed value for the potential of the expected value of the potential outcome if you have an immigration influx. The Mariel boat lift study uses the comparison cities to estimate the counterfactual average. And this is a weakness with this difference in difference setup. And we'll talk about other things later on, this synthetic control. that is sort of criticizing this sort of study. Uses comparison cities. Which cities should you use? Which cities are useful to compare with? If you're picking different ways, different cities, you can get the results you like. So choosing which is a counterfactual to measure the counterfactual it's hard to be objective in doing that. Okay. So they used cities. So David Carr used what he believed was good cities. Cities with similar trends in the unemployment rate before, and similar composition of immigrants and things like that. So based on covariates, he said, yeah, these cities are good comparisons to measure the counterfactual average for the Miami. So we need to estimate this for Miami after 1980 because this is not observed. So the difference in different setup identify causal effect by restricting the conditional means. So what we are saying is that the expected value of yi0 ct can be written as an additive separable function in the time and in the city average. So it's a parameter in time and it's a parameter for the city. So fixed effects for the specific city and a time. That is in the absence of immigration, unemployment rates or the sum of a year effect beta t common to cities and a city effect gamma c that is fixed over time. So you need to have something like this. The additive model pertains to the expected value of the potential outcome instead of y0 directly because the latter is 0, 1 variable. I talked about this just 2 minutes ago. To provide clarity, use the standard homogeneous treatment effect definition. So in this setup, you say that the expected value of y1 ct is equal to the expected value of yi0 c and t plus this treatment effect. So now we have a homogeneous treatment effect, but on the other hand, the treatment effect is defined at the expected level, at the aggregate level, not at the individual level. So it is, I mean, it's not the same, it's very far from the setup with the IV we looked at and also with the setup we looked at the regression discontinuity, because it's additive in the means. So you could still have heterogeneous treatment effects at the individual level. But at the individual level, this model is wrong because y1 is a binary variable. This is a binary variable, so it cannot be like this at the individual levels. This means that the unemployment status of individuals living in Miami and the comparison cities in 1979 and 1981 can be written as this, because this is what they are using. David Carr is using. He's using the differences between 1979 with 1981 when there was this influx. You can simply put it up like this. So you have a fixed effect at the time level, fixed effect at the municipal level, and then you have a difference in different estimator where MIT takes the value 1 if the individual is sampled at this time and was living in Miami after 1980. You see, I have YIT, so I have the indicator IT as sampling individuals living in Miami after 1980. So this is how you can see it. Okay, because we are sampling individuals when we do this kind of estimation. Individuals can move to different areas, but you are sampled. It's possible that this individual living in Miami after 1980 were not living in Miami in 1979. So you can use different individuals. You don't need to follow the same individuals. You are just using the individuals living in Miami before 1979. You are using individuals living in Miami after 1980. And for the same thing with the other cities, the comparison cities, the other in the same way. So the identifying assumptions are thus the functional form for this and the additive treatment effect at the city level given in equation 7. So this is sort of, you have a functional form for this, and you have an additive effect. It seems to be too strong assumption to assume that the effect in expectation would be the same in all cities across the US. So the effect most likely would be different if the influx is to other cities. Okay, so it is like a case study. It's hard to generalize to say that if the influx to another state in USA would have been the same, we would have gotten the same treatment effect. That is a little bit too. Well, you can discuss that. In the original papers, these kind of issues were not discussed, as I understand. It was a way of identifying a treatment effect, but the magnitude and things like that were not, sort of how to interpret it in other contexts was less discussed than they are today. Today, economists have a very good understanding of this, and this is often discussed. In difference in difference, the treatment is given at the group level, so error terms in regression models cannot be seen as an IID as is assumed in the analysis of randomized experiments. So in the difference in difference setup, the treatment is given at the group level, so all individuals in Miami are treated. Okay, all individuals in the other cities are not considered treated. But individuals in the states or in areas, they maybe have correlated behavior. It's not like a randomized experiments where you can see the error terms as being IID. So we need to pay attention to how standard errors are calculated when we do this kind of difference in difference modeling. For early influential papers on cluster inference, see Moulton 1990. For the difference in difference setup, see Donald and Lang. That's a very critical paper when you have very small groups that are being treated. And I cannot go through this, but it's criticizing sort of the inference procedures. Bertrand et al. Was a very influential paper to change the attitude how to do inference using difference in difference settings. They have a simulation study, and they also go through sort of a real. It's basically a simulation study. For a review of the literature, you can look at Cameron and Miller 2015. So today there is a tradition that you are using sort of bootstrap inference when you do this. At least when you have few groups, when you have few groups that are treated, then one can do some kind of bootstrapping. I cannot go into details with this. This is a large literature of how to calculate the standard errors. The initial papers were just analyzing using difference in difference, analyzing the data like it was from a randomized experiments. It's clear that the standard errors were underestimated. That means that they drew too strong conclusions from their studies than what they could do. This paper by Donald and Lang are really, basically saying that if you just have 2 time periods and one treated group and one control group, you cannot do any inference. Of course, you can do that, but then you need to add assumptions about sampling, and how to do the analysis. You can do it, but it was at one time period, this was a destructive paper in some way. People were very negative about the difference in difference setup and the calculation of the standard errors. One question. Okay. No. Okay, synthetic control method have received quite a lot of interest. That is combination of difference in difference and what I would say matching. So it's a combination of, but not really matching. It's more like, I don't know if you've heard if Don talked about, he don't like weighting estimators, but with matching, with this Rubin causal model, instead of matching individuals, you can use weighting estimators. You find weights, and then you are weighting the estimator instead of finding matching individuals. Here, this is a combination of a weighting estimator and a difference in difference setup. And it utilizes longer sequences of pre-treatment measurements in the analysis in general. Like just to, for instance, if you had something like this, you have 10 time periods before a treatment. Well, then we can utilize the fact that we have many pre-treatment observations in the analysis, in a difference in different analysis. So I just illustrate this so that you are aware of that this method can be used, and can be very. This is also to some extent like the regression discontinuity design, based on it provides you with quite convincing results because you can show the results graphically. So Abadi et al. 2010, they were estimating the effect of California Tobacco Control Program, and it's published in the Journal of American Statistical Association. So here it's a little bit the same as the graph I just showed you with the women and males incomes. So you have California here, smoking. So I think this is per capita cigarette sales. Yes. So it's per capita cigarette sales, and then they have the rest of the US. Okay, so this is the rest of the US. And here is this proposition where they it was tobacco control program. I think it was that they prohibited they were not allowing, for instance, advertising of tobacco or smoking, as I understood. There was some other things as well. So we have 50 states in USA. Okay, so this figure shows all of the other 49 states, something like that, 49 states. So this is the average of 49 states. One could have done like David Card did with this unemployment and marital boat lifts, to pick out states that have similar trends of per capita cigarette sales before. So if one could find states that have similar patterns for that, like 4 states, well, then we could have simply picked out these 4 states and then see what would happen after you have this proposition 99 implemented in California. But what they do in this synthetic control is to have a linear program to pick out weights to get the same trend before. So picking out states to get a weighted similar pattern as for California before you have this change in this proposition. So instead of picking up 4 states that you believe would be good controls, they are trying to estimate weights using linear programming to get similar trends, and then you look at what happens after. So this is what they do with this synthetic control. So instead of picking up real controls, they create something synthetic by finding different weights. It's like a matching strategy, trying to find out sort of states that are similar to California, but not picking out exactly, so that not picking out like using pre-treatment trends to say that, oh, it's these 4 states that are similar to California. Instead, they are estimating weights, and by that, from these estimated weights, they get a synthetic control to California. And this is what you see here. And after, they estimate the effect without any model. So they have a model here before, based on sort of this weighting estimator that is derived from linear programming. And here is just outcome data for the synthetic control and for California. And what you see here is, yeah, they are similar, but after this proposition, there is a sharp decrease in the per capita sales of cigarettes in California that differs from the trend in cigarette sales in this synthetic California. And it's not easy to do inference. So what they do when doing inference, they do Fisher randomization tests. So they do this by estimating this California. And then they redo things and estimate the control states by randomly drawing this over and over again. So this you get by different synthetic controls. You see the variation. You see the variation by doing this repeatedly, by removing some states and throwing and adding some states. They can estimate sort of under no treatment effects. So this is the control states. They redo the synthetic controls for the control states that did not have this reform. And then they see that this is the variation you get from our method. And what you can see is sort of this treatment effect that we observe here is one of the less likely effect, one of the least likely events we can observe. There are some other that is also very dramatic here, but this is one of the most extremes. This is a Fisher randomization test done sort of, it's a non-traditional Fisher randomization test, but this pattern is extreme in comparison to all other sort of models that we do, that we know there should not be any treatment effect here because there is no proposition for these other states. So they redo this by control states. So the synthetic control is a case study method, but can be encompassed to the situation with multiple treated units and thus to identify an average treatment effect for a population. The suggestion made in Abadi et al. Is that of aggregating the outcomes of all treated and thus to use the same synthetic control weights for all treated units. Other strategies have been developed, for instance, by Brodersen. An alternative is Schultzberg 2018. This is my PhD. He was my PhD. And he proposed a matching strategy and a Bayesian way of analyzing it to estimate the average treatment effect of the treated. I kind of like this, but he has not been able to publish it yet, but I guess he's working on it. So this is explicitly a matching strategy to estimate the average treatment effect of the treated. So if you go to Uppsala University, you can look at this, and perhaps you can think of a way of extending on what he do, and perhaps also have a better proof of the procedure than what he had in this thesis. Yeah, I think that was everything. I have 2 questions. I know that the difference in difference may need covariates, and covariates should be pre-treatment ones. My question, should we only use the pre-treatment values, say t minus 1, 2 of those covariates in a panel setting? Thanks. Yeah, I mean, this is related to sort of in the difference in difference world. There are applications where they include covariates into the regression model, and they also include covariates measured after the treatment. So they simply include covariates. They are arguing why we should control for the covariates. And in that case, you need to also be quite clear that you need to control, for instance, there is a reason to control for things after the treatment. So there exists difference in difference papers that control for covariates measured after the treatment, like controlling for demography in the areas and things like that. But then you in some way need to discuss why you need to control for these covariates. Does it have to do with bias, or has it to do with only efficiency? If sometimes these control variables are affected by the treatment, and if you add them, then you will get the bias treatment effect of the overall effect. But perhaps you are also interested in removing effects that is caused through these covariates. And then perhaps you should add them in the regression model. I hope you understand. You need to be clear on what you are trying to estimate. This is, of course, related to sort of mediators and things like that. There is no clear answer on this kind of question. It depends on what you are trying to estimate, and you need to think about it. Should I include covariates afterwards? And do I need to do it? If you add covariates that are measured after the treatment, you need to discuss why. I think that. So my advice for students is that follow sort of the idea from the Rubin causal model, in that you need to be clear. It's easy to do this setup if you control for covariates that are measured before. If you add covariates that are measured after, and you need to do it, you need to discuss this very clearly. People do it. Sometimes papers are published without people are discussing it clearly. So there are, I mean, it doesn't mean that it's correct just because it's published in a very good journal. Yeah, the bottom line, you need to think about and be clear why you add covariates that are measured after the treatment. And if you can justify it, then add it and discuss sort of potential endogeneity, potential bias in your estimator if you do it. But if you say that I would like to remove potential effects from this covariate that is also affected, yeah, then you are in the mediator world with mediators. So then you need to read up on that. Yeah, so there is no easy answer. There is no easy answer. But in general, it's if you don't need to add covariates measured after the treatment, it makes things much more clean. What's your opinion in terms of methods such as synthetic control compared with difference and RD? Which do you see as a more promising method of research? Difference in difference, I think if you do methodological work, it's almost everything is done in difference sort of. There are still things that are open when it comes to the combination, the synthetic control, I think, methodologically. I haven't been reading up. There are some papers coming out at the moment. I saw some papers just recent about the synthetic controls. So synthetic controls are basically sort of an adoption or improvement of the previous difference in difference setup, I would say. It was introduced by Abadi and Heinmüller and so on for being a more objective strategy. I think that is objective in the sense that, okay, Card was criticized for picking certain states as a comparison. Why did he pick these 4 states as a comparison? I think it was 4 states in contrast to others. So they wanted to have a strategy that objectively picked control states. So that was one way of introducing the synthetic control. I think the synthetic control is today we have, if you are doing things using data from internet, like with this IT, you have individual data that we are measuring over time. Like this paper by Schultzberg, he had paper on electricity consumption at individual levels. And he wanted to use all these pre-measured variables in a matching strategy. And he didn't want to do the synthetic control and I think that was not the right thing to do, because he was interested in the average treatment effect of the treated. It was not a case study. It was really trying to estimate the average treatment effect of the treated. So I think with this availability of the longitudinal data means there is rooms for methodological development with that type of data. That this type of data we did not have like 10, 15 years ago even. Now there is a lot of this type of longitudinal data, and how to use this kind of measurements in an efficient way for analysis. I mean, this paper that I showed you here is one example of this, and this paper is cited like it was published in 2016, but I think we have something like 500 citations now. It was just that we could follow individuals over time, and it's a very simple strategy for doing it. And we discuss also the methodological sort of what is needed for us to identify a treatment effect in this case with this type of data. No one had done it before. Instead, they have used very limited set of data, but all this type of data is available in Sweden, meaning that we can follow individuals over time, and this is very useful for identification strategies. Tons of papers use the similar methods in empirical errors. Could you suggest what is the trick to hit the good journal? Yes. Yeah. I think it was quite easy to publish in good journals with this type of quasi-experimental designs that I have been going through now, like 15, 20 years ago. But now there are tons of these type of papers. So identification is not sufficient anymore, I would say. So if you have a clear identification strategy, but that you also can explain more than it's a treatment effect. Why does this treatment effect occurs? What is the cause behind something? Many times it's just a treatment effect. There is this effect that is of this size, but we don't know why. So today, it's not enough to just have a cool identification strategy. You need really to explain more about why you get these treatment effects using this type of strategies. I think if you have cool data from China, that you still have quite good opportunities to publish in good journals, because there is still a large interest in understanding sort of things in China, because we can learn from the differences we have with the institutions in China. I think so, but I don't know. No, I'm a little bit. Sorry, I cannot say more than that. It has been a cool identification strategy is not enough anymore. I think that to publish in the top journals, you need to do something more. If you can combine these kind of cool identification strategies with more structural modeling, so that you can explain why different effects occurs, you have a really good chance in publishing in a top journal. I saw that PSM plus differently proposed by Heckman et al. Is popular. My question is that there are unobserved time invariant factors in a situation that is supposed to. In this situation, why can PSM be employed? PSM is only valid under selection on observers. I'm really baffled. Could you please tell me your opinions on this? So, yeah, I usually talk about this as well. And that's correct. Why can't I? Oh, let's see if I have. Don't I have this? Yeah. Yeah. So the main paper, I think, when looking at what they are doing in this one, combining matching with the difference in difference strategy, is by this paper by Petra Smith and by Petra Todd and Jeffrey Smith from 2005 in Journal of Econometrics, where they explain more clearly what they are doing with this combined matching and difference in difference strategy. But if we have this, let me see. Yeah, okay, we take the simplest case. So this is the most simple difference in difference estimator. Here you take the mean of all individuals observed in time period 2 after the treatment. Here you take all individuals that are observed in the first period. And here you take all individuals in the second period and all individuals in the first period. Okay. If you don't believe that the two populations are really the same, so they differ. So the population in the B, in this B group differs from the population in A. Then perhaps if you have a situation where you have a reform that making these individuals similar on observed characteristics may improve on the estimation. Okay, so by taking all, and these two groups differs a lot, perhaps you get a very imprecise estimate. So you can use the propensity score matching or a matching estimator to make these two groups similar based on observable characteristic. Okay, so you estimate this for the group that is treated, a propensity score. Then you find similar individuals in the second group, and you find similar individuals in the first group. So you say that I make them similar, but it's still, when you do the difference in difference, it could still be things that are different between the two groups that are not observed. So you are combining a selection on observables estimator with a selection on unobservables estimator. So you need to still have some assumptions why making this, why you remove the unobservable part in this. I agree, it is a little bit complicated or a little bit confusing. So in this paper by Smith and Todd, they have an individual treatment. So in this case, by the Smith and Todd, they have a treatment that is labor market training. It's not really a policy. So you have two groups of individuals, two types of groups. One enter into labor market training program, and other group do not enter into the labor market program. But they have observations of the groups not entering labor market program before. And then they have a group of individuals also for both groups. And in this setting, when there is a choice of being treated or not, it makes more sense of combining propensity score matching with the difference in difference setup. When you have a policy reform for like one municipality or one state or something like that, where there is no choice of the individuals to be treated or not, it makes less sense of combining these type of strategies. I hope you understand this difference. Was that a clear? Yeah. So it depends on what type of treatment you are looking at as well. We all know that the methods of difference has been widely used. So what else is new in this method, or what could be improved about this method? Thanks. Yeah, as I said, I think I cannot see any methodological development now with the difference in difference strategy. There was one interesting thing at the individual level with the difference in this difference, and that is called the changes in changes strategy, introduced by Susan Athy and Guido Imbens. So that is another strategy of doing difference in difference that doesn't need the functional form assumption like this, that it's an additive separable effect. But on the other hand, it builds on a rank preserving transformation, which is quite strong assumption. That was interesting, and they did quite a lot of methodological in trying to do something more with it, but it's almost never applied. And one reason is that I think is that you cannot really believe in this rank preserving assumption that is needed for this changes in changes strategy introduced by Susan Athy and Guido Imbens. I get a bit, I need to read Smith and Todd. Yes, please read Smith and Todd. And the whole thing is that this is a valid strategy if you are interested in treatments that individuals can choose. Basically, if you have reforms affecting everyone in the society or in the state, I think then this matching strategy may not be so relevant.
Hey Pierre, I have a question.
Oh, it's Jonny. Hello, Jonny. You are here.
I have a question on the synthetic control method.
So
when people choose weights, do they always use some kind of optimal weights, or do they kind of sample the weights from some kind of distribution?
They don't choose. They have, it's a linear program they put up.
So it's optimized, kind of, yeah.
Yes, it's based on the optimization. Yes, it's based on optimization procedures. Yes, but you can, but you have parameters in this optimization strategy. So by putting different parameters in this, you can get whatever weights you like. I had 2 PhD students looking at this, and they were quite critical, and especially about the inference strategy that they were using.
Yeah, so if you get different type of weights using different parameters, do they yield similar conclusions, or I guess that's not guaranteed?
No. So when we started to look at this method together, I was also involved to some extent. I mean, it was all sort of advertised as this is the objective method of doing difference in difference if you have longitudinal data. You can also add covariates to this, but you could get whatever weights and results you like depending on how you set this parameter. So it's much less objective. But I guess this literature has developed to some extent. So people are aware of this, of course. So trying to make it even more, I mean, to make it more objective, I would expect that, how to do this. Yes, but no, it was an oversell of this method, definitely in this 2003 paper and also in this 2010 paper. Yes, no, they were overselling this objectivity. That's quite clear. Yeah, no, very relevant question. Yes.
Yeah, thank you.
Okay, for audience, do you have more questions? We have a lot of questions in the chat, but I'll stop now. Seems like there are no more questions. Okay, so thanks Pierre for the wonderful lecture today and for all the patience on answering this. Oh, there is another question.
A patient is not fair. It's some of it's I cannot. Yeah, it's very general questions, and it's hard for me to answer some of them. What's the difference between difference and IV? There was 2. Dear professor, synthetic, could we use estimate the effect of a policy on the US state by using the cities as the donor pool, which are not located in that state? Could we use estimate on the US by using donor pool, which was not located in that? What you are saying is that you would like to estimate the effect in a particular US state, and then using cities as donor pool, which are not located in that state. As I interpret the question, you are saying that could we estimate the effect of a policy in a US, in one specific state, and then using cities as donor pool, which are not located in that state? Yeah, I think you could do that. I think one could do that, of course, but you need to understand the institutions and why you can do that. So it requires you to really understand sort of the institutions, how they differ between the states, and why you can use donor pools from another state. This is basically what the paper by Aschenfelter and Carr did when they were estimating the effect of the minimum wage on employment and wages. So they had this difference in different setup. So they have one state, New Jersey, that was affected by this minimum wage. And then they used fast food restaurants in New Jersey, and then they used fast food restaurants in a neighboring state, which must have been, I forgot the state name. So they used fast food restaurants, one in the affected, and then fast food restaurants in another state that were not affected by this. So of course you can use also, if you are interested in a policy reform in one city, in one state, and then you can of course use depending on, but yeah, you can do that, but you need to think about so that there is no institutional changes that may affect your results between institutional changes in the states that is not affected, and that the institutions are comparable when it comes to the outcome variable that you are trying to measure. Yes. What's the difference between difference and IV? Yeah. I mean, there are substantial differences. I mean, there are papers that are combining difference in difference with IV, so I can see the question. I saw an explanation that company can be in instrumental. Yeah, I think this is what I was thinking of. So in some way you can think about the difference in difference as estimating the reduced form. So say that I'm sort of if we take the Jon Snow example, yeah, they have this factory that moved upstreams. All they can estimate is sort of the indirect effect of this contaminated water. So that's what you estimate with the difference in difference. So you estimate the effect on mortality by moving the water work upstreams. If I was really interested in estimating exactly the effect of contaminated water with cholera on mortality, then I could use the fact that they moved it upstreams as an instrument, given that I also could measure the amount of cholera in the water. So if I had a measurement of cholera in the water, then I could see how that changed sort of the amount of cholera in the water, and by that I could back out the effect of contaminated cholera water on the mortality rate. So this is just a treatment effect, sort of changing the position of the water work. And we don't really know exactly why you get changes into the mortality rate by moving the water work upstreams. But if you have a measurement of the cholera level on the water, you can do more. And that's what I'm talking about today. Even if you have a cool strategy, all you get is an estimate. If you could sort of have an instrumental strategy and really find out sort of what is it in this treatment that let me go back. If we take this late, perhaps I have no easy. I did not set this up. Yeah. Entropy, but I changed. This is sorry. Just this simple case. Okay. So what I'm saying is sort of, here I have a clear understanding what is the treatment, okay? And I can interpret beta 1. But due to heterogeneous treatment effect, I can only then, if this is a real valid instrument, I can only estimate the compliant treatment effect. On the other hand, I can estimate this direct effect of Zi on Yi. That's alpha 1. This is the intent to treat effect. So the question is, when is the intent to treat estimate of interest or not? If you are only interested in an intent to treat effect, that's fine. But in economics, we would really like to know the effect of the real treatment, because that may be perhaps of most interest. In the difference in difference setup, it's basically this intent to treat effect that we can estimate. And sometimes this is of large policy relevance, sometimes it's not. So if I take this example with these immigrants flowing into Florida, well, you get in Florida, you didn't get any effect on the unemployment rate from this great influx of immigrants. Well, that's interesting, but perhaps, as I said, this effect could be very different in other states, could be very different. So it's very hard to generalize from an intent to treat effect. So nowadays, what we would like to do is know more about why an effect occurs and why an effect does not occur. If we could be clear on why the effect did not occur in Florida from the influx of immigrants to Florida, well, then it's easy. Then we can perhaps more easily generalize from this quasi-experiment to other situations. The reason why it didn't occur was that the labor market in Florida was very special, something like that. You had already all these kind of Cubans living in Florida. They had a specific industry structure. They have very low wages. That's why it didn't occur. So I hope that was an answer to your question. You can see you can sometimes use the difference in difference setup to learn more than just estimating this ETT effect, the intent to treat effect. More questions. One assumption, allow SM, this synthetic control works, is the covariate convex. One assumption allow is the covariate convex. I kind of feel this assumption has some resemblance to positivity. It's likely to be violated in high dimensions. Yes. No, it occurs when people were using this in here at Uppsala. It was very popular here in Uppsala like 10 years ago, when a lot of people would like to use it, but it was not so easy. Many times it didn't converge, so it was less easy to work, and people started to be sort of more skeptical towards it. It's still, I think it's very interesting. I think it's very interesting, but they have problems, especially if you have a lot of covariates. That's quite clear. That's my experience with it, and I have not been working actively with it. I had PhD students working with it, and that's what they told me when they were trying it. Okay, Rui.
I guess we have finished all the questions here.
Yes.
Okay, thank you for the wonderful lecture today.
Oh, thank you.
And I think we all learned a lot from this. And I think I didn't share the slides yet, but is it okay to share the slides with the audience?
Yeah, I can send. I updated a little bit. I found some small things, so I can send you that. And yes, of course. No, I have some references in the end of this as well, so people may look at that. Yeah.
Okay. So I will distribute among the audience.
Yes. Yeah, thank you as well. It was really nice with all the questions, even though I got them written instead of communicated directly.
I can send you a list of the questions today, if you want.
What?
If you want, I can send you a list of the questions.
No, that's fine. That's fine. That's fine.
Okay.
Yeah.
Okay. So
Okay.
that's all for today.
Yes. Thanks a lot.
Okay. Bye bye.
Bye bye. Bye bye.